Please subscribe to support the channel. What if black holes didn't just appear after stars died, but instead, some of them were already here before the universe itself was born? Think about that for a second. The very objects we associate with collapsed stars and galactic cause might, in some form, have existed before time began as we know it. This isn't just a quirky what-if from science fiction. It's a genuine cosmic mystery that has captured the attention of some of the world's greatest physicists. These entities are called primordial black holes, and if they truly exist, they could completely rewrite our understanding of the cosmos. They might tell us not only about the birth of the universe but about what, if anything, came before the Big Bang. The Big Bang theory has long stood as the dominant narrative. The universe began about 13.8 billion years ago, expanding from an unimaginably hot and dense point into the cosmos we observe today. But when we start talking about black holes that could predate even this moment of creation, we are stepping into uncharted territory. It forces us to question the very framework of cosmology itself. Was the Big Bang truly the beginning? Or was it just the latest chapter in a story that stretches infinitely backwards in time? And if black holes really did exist before the Big Bang, then they might not just be astrophysical objects, they might be literal fossils of a universe that came before ours. To frame the scale of this mystery, we need to appreciate what black holes actually are. At their core, black holes are regions of spacetime where gravity has become so intense that nothing, not even light, can escape. They warp the very fabric of reality, bending it into a point of no return known as the event horizon. From the outside, they are invisible. We can only detect them by their influence, how they bend light, how they devour stars, or how they send ripples through spacetime when they collide. They are, in a sense, nature's greatest magicians, hiding infinite depths behind a curtain that no one can pull back. But primordial black holes? Those are something altogether stranger. Unlike the ordinary black holes formed from collapsing stars, these are theorized to have been born in the earliest fractions of a second after the Big Bang, or possibly even before. They are not the corpses of stars but ancient survivors of the most extreme cosmic conditions. Some could be incredibly tiny, smaller than an atom yet packing the mass of a mountain. Others could rival the size of black holes at the centers of galaxies. And if they truly exist, then they might hold answers to some of the most perplexing questions in modern physics, like what dark matter is, how galaxies formed, and whether the Big Bang was really the beginning. This is the enigma we'll be exploring in depth, the idea that some black holes may have existed before the universe itself. Over the course of this journey, we'll unravel how they might have formed, why they matter, what evidence scientists are searching for, and how this mind-bending idea could forever reshape our understanding of time, space, and reality itself. To understand why primordial black holes are so fascinating, we need to pause and get comfortable with what a black hole actually is. People often imagine them as monstrous cosmic vacuums sucking up everything in sight, but that's not quite accurate. A black hole is, at its simplest, a place in space where gravity has gone completely out of control. Normally, gravity is what keeps planets orbiting stars, what pulls an apple down from a tree, and what holds galaxies together. But in the case of a black hole, gravity has become so strong, so extreme, that not even light, the fastest thing in the universe, can escape its pull. That's why they're called black holes. Once light goes in, it never comes out, leaving only darkness. Think of it like this. Imagine a trampoline. If you put a bowling ball in the middle of the trampoline, it will make a dip, and smaller balls roll toward it. That dip is a way of picturing how mass bends space. Now imagine replacing the bowling ball with something much heavier, like a cannonball, and the dip becomes steeper. Eventually, if you could make the object heavy enough, the dip would be so steep that it wouldn't just curve down, it would become a bottomless pit. That bottomless pit in the fabric of space and time is a black hole. Scientists describe a black hole's point of no return as the event horizon. This is like the edge of a waterfall. Once something drifts past it, there's no turning back. Inside the event horizon, physics as we know it breaks down. At the very center lies what's called a singularity, a point where density is infinite, where the laws of space, time, and matter as we understand them cease to make sense. It's one of the most mysterious ideas in physics, because even our best theories, like Einstein's general relativity, fail to explain what truly happens at that singularity. But here's the subtle thing. Black holes don't always form by swallowing everything in sight. A black hole forms when mass is compressed into a tiny enough region that its own gravity collapses it further. The most common way this happens in our universe is when massive stars run out of fuel. A star shines by burning nuclear fuel, but eventually, the fuel runs out, and gravity takes over. The star collapses inward, and if it's massive enough, it doesn't just become a dense neutron star, it collapses all the way into a black hole. So, in everyday astrophysics, when we talk about black holes, we're usually talking about these stellar black holes born from dying stars. Some are only a few times the mass of our Sun. Others, through collisions and growth, can become giants millions or even billions of times more massive. These are the supermassive black holes that sit in the centers of galaxies, including our own Milky Way. But regardless of their size, the concept is the same: an object so dense that nothing, not even light, can escape its gravitational pull. Yet, to really appreciate why primordial black holes are such a mind-bending idea, we have to appreciate just how alien black holes already are. Even though scientists can explain their mechanics in terms of gravity and relativity, there's still a sense of paradox about them. From the outside, a black hole looks deceptively simple. If you were to describe one, you'd only need three things: its mass, its spin, and its charge. That's it. This is often summed up by the phrase "black holes have no hair," meaning, no matter how messy or complicated the matter was that fell in, the black hole itself forgets all of that information and is described by just those three properties. If you threw in a star, a planet, or even a library of books, the black hole doesn't care. From the outside, it all looks the same. But that leads to one of the greatest mysteries in physics. If black holes erase information in this way, then where does the information about what fell into them actually go? Quantum mechanics insists information can't just disappear. General relativity says it does. This clash between two of the deepest theories in science is known as the black hole information paradox, and it remains unresolved. Already, black holes force us to confront contradictions in our understanding of reality. Now imagine taking this already paradoxical object and saying some of them might not be tied to stars or galaxies at all, but instead might be leftovers, or even precursors, from the very birth of the cosmos. That's what makes the primordial black hole idea so intriguing. If ordinary black holes are already strange and mysterious, primordial black holes take that strangeness to a whole new level. They would not just be the products of cosmic evolution, they would be ancient artifacts, potentially even older than the universe itself as we understand it. To put this in perspective, think about the scales involved. A black hole the mass of our Sun would have an event horizon only about 3 kilometers across. That's smaller than a typical city, yet it would contain all the mass of a star so large it dwarfs everything in our solar system. If you shrink the mass even further, down to something like the mass of a mountain, the event horizon becomes microscopic, smaller than an atom. And yet, it's still a black hole, it still has an event horizon, it still traps light, it still bends space and time infinitely. On the other extreme, supermassive black holes can be billions of times more massive than the Sun, with event horizons larger than our entire solar system. The spectrum of black hole sizes is staggering, and primordial black holes, if they exist, could sit anywhere on that spectrum. This makes them not just fascinating, but also potentially fundamental to understanding the architecture of the cosmos. When we simplify the definition, regions where gravity is so strong not even light can escape, we're really only scratching the surface of their strangeness. Black holes embody contradictions between our deepest theories. They behave in ways that defy intuition, and they hold within them questions about the fate of matter, the flow of time, and the limits of knowledge itself. And it's from this foundation that we can now begin to see why the distinction between ordinary black holes and primordial ones is so important. Because if normal black holes are already born of collapse and death, primordial black holes are born from creation, or perhaps from what existed before creation. That difference changes everything. So far, we've built a picture of what black holes are in their most basic form. Regions where gravity has gone completely unchecked, trapping everything, even light. But not all black holes share the same origin story. This is where the difference between the regular black holes we're familiar with and the mysterious primordial black holes becomes so essential. Understanding that difference is key to appreciating just how revolutionary the primordial black hole idea truly is. The most familiar kind of black hole is the stellar black hole. These are the black holes that form when a massive star reaches the end of its life. Stars shine because nuclear fusion in their cores balances out gravity. For billions of years, hydrogen is fused into helium, releasing energy that pushes outward, preventing the star from collapsing under its own immense weight. But nothing lasts forever. Eventually, the star runs out of fuel, and when the outward pressure disappears, gravity takes control. For smaller stars, the collapse halts at the stage of a white dwarf or neutron star. But if the star is heavy enough, at least 3 times the mass of our Sun, gravity overwhelms all resistance, and the star collapses into a black hole. That's the typical black hole you'll read about in astronomy books or hear described in science documentaries. The corpse of a once brilliant star, crushed into a singularity. Stellar black holes, then, are products of death. They are born from the cycle of stellar evolution, requiring billions of years of cosmic time to form. They come in sizes ranging from a few times the mass of the Sun to perhaps dozens of times that. They are relatively common, sprinkled throughout galaxies, detectable when they feed on companion stars or when their collisions send gravitational waves rippling across space. They fit neatly into the cosmic story we already tell ourselves. Stars live, stars die, and some stars die so dramatically that they become black holes. Primordial black holes, however, are radically different. They don't require stars at all. They don't even require galaxies. They are theorized to have formed in the earliest instance of the universe, in the chaos following, or perhaps even preceding, the Big Bang. Picture the universe when it was less than a fraction of a second old, filled with unimaginable densities and temperatures. In that seething, unstable environment, even the tiniest fluctuations in density could have been enough to cause regions of space to collapse into black holes. These would not be the corpses of stars, they would be something else entirely, fossils of the conditions of the newborn cosmos. This is why primordial black holes are so captivating. If stellar black holes are the ashes of burnt-out stars, primordial black holes are the relics of creation itself. They would have formed long before the first stars were ever born, in an epoch when matter was still a swirling plasma soup. Some theories even suggest they could have existed before the Big Bang, if the Big Bang was not the beginning but rather a transition from a previous phase of the universe. That alone sets them apart from the black holes we normally think about. They may not be tied to the death of stars, but instead to the very birth, or rebirth, of the cosmos itself. Another way to appreciate the distinction is to consider the range of sizes. Stellar black holes tend to fall within a predictable range, a few to dozens of solar masses. Supermassive black holes, which we see at the centers of galaxies, probably grew from smaller seeds, either stellar remnants or other dense objects that merged and fed over billions of years. But primordial black holes could be almost anything. Because they don't rely on stars, their masses could vary wildly. Some might be as tiny as an atom yet still hold the mass of a mountain. Others might be thousands or millions of times the mass of the Sun. They could fill in all the gaps in between, forming a spectrum of possibilities that no ordinary black hole could match. And this leads to one of the most fascinating implications of primordial black holes. If they exist in large numbers, they might make up some, or even all, of the mysterious dark matter that we know must exist but cannot see. Regular stellar black holes cannot possibly account for dark matter. There simply aren't enough of them. But primordial black holes, scattered throughout the cosmos since the dawn of time, could, in theory, be lurking unseen, providing the invisible gravitational glue that holds galaxies together. That possibility alone makes them vastly different from the black holes we already know. It's also worth pointing out that while stellar black holes require billions of years of stellar life cycles to form, primordial black holes would have formed instantly, within the first second of the universe's life. Imagine that, black holes existing before stars, before galaxies, before planets, before anything we would recognize as the cosmos we see today. That flips the script on how we think about black holes entirely. Instead of being latecomers in the universe's story, they could have been the very first actors on the stage. To highlight the contrast even more, let's think about how we detect these different kinds of black holes. Stellar black holes can sometimes be spotted indirectly when they interact with matter around them, when they strip gas from a nearby star or when they crash into another black hole, releasing gravitational waves. But primordial black holes would be nearly impossible to detect by those same means. Many of them could be wandering invisibly through the universe, dark and silent, detectable only through their subtle gravitational effects, like bending light from distant stars or leaving tiny fingerprints on the cosmic microwave background radiation. In this way, their very elusiveness is part of what makes them so compelling. So the difference comes down to this. Stellar black holes are the end products of stars. Primordial black holes are the potential relics of the beginning of everything. One is born in death, the other possibly born in creation itself. One is predictable, the other is speculative and wide-ranging. And if primordial black holes really do exist, they may hold the keys not just to the history of our universe but to whatever came before. To understand how primordial black holes might have come into existence, we have to take ourselves back, far back, to the very earliest moments of the universe. We're not talking about millions or even thousands of years after the Big Bang. We're talking about the first second, the very first fraction of a second, when reality itself was still settling into what we now call space and time. The early universe was not calm, structured, or familiar. It was chaos, unimaginable density, unbearable heat, and wild fluctuations of energy. This was the kind of environment where the rules of ordinary physics gave way to something far stranger, and it's within this tempest that primordial black holes could have been born. Right after the Big Bang, the universe was in what's called a Planck era, lasting only up to about 10 to the power of -43 seconds after the beginning. At this point, everything was compressed into an almost inconceivably tiny volume. The density was so great that gravity itself was operating on quantum scales, and we don't even have a complete theory that fully describes this moment. Our current physical laws break down under such conditions, but what we can say is that the universe was a kind of frothing sea of quantum fluctuations, where space-time itself rippled and buckled like a stormy ocean. Then came a rapid inflationary period, where the universe expanded exponentially in an instant. During this time, the extreme energy density and sudden stretching of space created tiny irregularities in the distribution of matter and energy. Imagine a balloon being blown up extremely quickly. No matter how smooth it looks, there will always be tiny imperfections on its surface. For the universe, those imperfections were density fluctuations. Some regions had slightly more matter than others. Normally, these little variations would later grow into galaxies and clusters under the influence of gravity. But in those very early instants, if a patch of the universe was just a little too dense, gravity could have instantly overwhelmed it, causing it to collapse into a black hole right then and there. This is the essence of the primordial black hole hypothesis. Unlike stellar black holes that need stars to live and die, primordial black holes could have formed almost immediately, birthed from the sheer density and energy of the young universe. The early cosmos was like a cosmic forge, and in certain spots, it may have compressed matter so tightly that black holes formed before there was ever such a thing as a star. To really grasp how extreme those conditions were, consider this. In the first microseconds after the Big Bang, the universe was hotter than 1,000,000,000,000 degrees. That's not just hotter than the core of a star, that's hotter than anything we can even simulate in the most powerful particle accelerators on Earth. In fact, the entire universe was essentially a giant particle accelerator, smashing quarks and gluons together in a dense plasma soup. This was a state of matter called a quark-gluon plasma, something so alien and energetic that atoms as we know them couldn't even exist yet. It's within this almost incomprehensible environment that the seeds of primordial black holes could have formed. Imagine a tiny region, perhaps only the size of an atomic nucleus, but denser than a mountain compressed into a single grain of sand. That's the kind of density fluctuation we're talking about. And if gravity got the upper hand, that region could have collapsed instantly, forming a black hole that still exists to this day. Some might have been microscopic, some might have been massive. The variety would depend on the scale of the fluctuations in those early instants. Another fascinating aspect of this idea is how it connects to the universe's later structure. The early fluctuations in density didn't just potentially create black holes, they also became the blueprint for the cosmic web we see billions of years later. Those small imperfections grew under gravity's pull, eventually forming galaxies, stars, and planets. In a sense, the same process that could have created primordial black holes is also the process that shaped the very architecture of the cosmos. The difference is that some regions tipped over the edge into collapse, while others expanded and evolved into the structures we now observe. To get a sense of scale, scientists have modeled what kinds of black holes could have formed under those conditions. Some could be as small as the mass of a mountain, tiny by cosmic standards, yet still enormous compared to anything we could handle here on Earth. Others might have been as massive as the Sun, or perhaps even much more. The distribution of sizes would depend on the specifics of the density fluctuations and how inflation unfolded. That means if primordial black holes exist, they could be scattered across the cosmos in a vast range of sizes, many too small or too faint for us to detect easily. And here's another remarkable thought. The early universe was expanding at breakneck speed, but in those first moments, regions of matter that collapsed into primordial black holes would have essentially dropped out of that expansion. They would have become stable, compact objects while everything else was stretching and cooling. That makes primordial black holes unique survivors, objects that froze in place while the universe around them transformed radically. If they exist, they are not just astrophysical oddities. They are relics, time capsules that carry with them the conditions of the early universe. It's hard to overstate just how exotic the early universe was. Every second mattered. In the first second after the Big Bang, forces that are now distinct, gravity, electromagnetism, and the nuclear forces, were still interacting in ways we barely understand. In that fleeting instant, the building blocks of everything we know today were taking shape. And in that crucible, black holes may have formed not as an endpoint of stellar life, but as the very first objects of existence. So while stellar black holes are children of time, primordial black holes, if real, are children of creation itself. They represent the possibility that even in the most chaotic, high-energy environment imaginable, gravity could carve order out of chaos, leaving behind compact objects that outlived the very era they were born into. If we could find them, they would be direct witnesses to the universe's infancy, carrying secrets no other cosmic object could. When scientists use the word primordial to describe these black holes, it's not just a poetic flourish, it has a very specific meaning. In everyday language, primordial means ancient, existing from the very beginning, untouched by later processes of change. In the context of cosmology, primordial refers to things that existed before the familiar structures of the universe had even formed. Before galaxies spun into existence, before the first stars ignited, before planets and moons circled in their orbits, primordial black holes, if they exist, would already have been there. That distinction is vital. Ordinary black holes are born after stars live out their lives, collapse, and die. They depend on the existence of stars, which themselves depend on galaxies and long epochs of cosmic evolution. There's a timeline built into the story. Stars form hundreds of millions of years after the Big Bang, live for billions of years, and then collapse to form black holes. But primordial black holes don't follow this timeline. They would have skipped all of it. Their birth would have happened at a stage so early that the universe had not yet cooled enough for atoms to even form, let alone stars or galaxies. Think about what that means. Primordial black holes would be older than the first light. They would be older than the cosmic microwave background radiation, which was released about 380,000 years after the Big Bang. They would be older than the first hydrogen atoms, which had to wait until the universe cooled to stable temperatures. They would, quite literally, be the oldest physical structures in the universe. In fact, if they exist, they might be the oldest surviving objects in all of reality. The word primordial also signals that these black holes carry information about the universe at its most raw and unshaped stage. Before the complexity of stars, chemistry, and life, there was only density, energy, and fundamental forces interacting in extreme ways. Primordial black holes would be relics of that era, like fossils trapped in the bedrock of space-time. They wouldn't just be astrophysical curiosities, they'd be direct evidence of conditions that no telescope, no particle collider, and no other experiment can reproduce today. To study them would be like holding in your hand a shard of the very first moment of creation. It's helpful to think of this in terms of cosmic history. The first 100 million years of the universe are often called the cosmic dark ages. There were no stars yet, no galaxies, no sources of light, just clouds of hydrogen and helium drifting in darkness. From our perspective, this was a time when the universe was almost featureless. But if primordial black holes formed before or during this epoch, then they would already have been shaping the landscape of the cosmos before the first stars even lit up. They would have been the true first architects, influencing how matter clumped together and possibly even serving as seeds around which galaxies later formed. Calling them primordial also underscores their uniqueness. Stars, galaxies, planets, All of those are secondary features of the universe. They're products of processes that took millions or billions of years to unfold. But primordial black holes would be primary features. They would have arisen directly from the raw physics of the Big Bang itself. They wouldn't just be things within the universe, they would be tied to the act of the universe coming into being. That makes them fundamentally different from everything else we know. This is part of what excites cosmologists so much about the idea. If primordial black holes exist, they would give us a direct probe into an era of the universe that's otherwise almost completely inaccessible. The early universe left very few traces we can study. The cosmic microwave background is one. The distribution of galaxies today is another. But beyond that, it's mostly guesswork. Primordial black holes, however, would be fossils, unchanged, untouched, still carrying with them the conditions of the moment they were born. They would be a window into a chapter of cosmic history that is otherwise closed to us. And this is why the terminology matters. When we say primordial, we're not just saying very old. We're saying older than stars, older than galaxies, older than atoms, older than light itself. We're saying these objects, if they exist, could be the very first structures ever to emerge in the universe, the seeds sown at the dawn of everything. They are not the children of the cosmos, they are its ancestors. Now we come to one of the most daring and mind-stretching ideas in modern cosmology. What if primordial black holes didn't just form in the seconds after the Big Bang, but instead had been around before the Big Bang ever happened? This suggestion sounds almost impossible at first, because the Big Bang is usually described as the very beginning of everything: space, time, matter, and energy. In that picture, there can't be a before because time itself begins there. Yet as radical as it sounds, some physicists have begun to seriously consider the possibility that primordial black holes might predate our universe, existing as ancient relics that somehow survived a transition from an earlier cosmic phase into the one we live in now. This is speculative, but here's the reasoning. The Big Bang theory is fantastic at explaining what happened after the universe began expanding 13.8 billion years ago. We can trace the formation of light elements, the cosmic microwave background radiation, the birth of stars and galaxies. All of it fits. But the theory struggles with what happened at the singularity, that first instant when everything was infinitely dense and hot. Physics as we know it simply breaks down at that point. So naturally, scientists have asked, what if the Big Bang wasn't truly the beginning, but just a transformation, one event in a longer cosmic story? In that context, black holes become especially intriguing. Unlike stars, planets, or galaxies, black holes are incredibly resilient structures. Once formed, they are astonishingly hard to destroy. Ordinary matter can be torn apart, radiation can disperse, galaxies can collide and merge, but black holes persist. If the universe underwent a catastrophic collapse before the Big Bang, if there was a prior cosmos that ended in some violent way, it's not inconceivable that black holes from that earlier universe might have survived into ours. In other words, they could be cosmic refugees, carrying information across the boundary of universes. Think of it like a fire. Most objects are consumed by the flames, but a diamond might survive, carrying traces of its earlier form. Primordial black holes, in this analogy, would be the diamonds that survived the fire of a prior universe's end, passing through the Big Bang into the cosmos we inhabit now. This idea reframes them not only as fossils of the early universe but as fossils of a universe that came before ours. Some theoretical models even suggest mechanisms by which this could happen. For example, in certain bounce cosmologies, the universe doesn't begin with a singular Big Bang but instead cycles through phases of expansion and contraction. A prior universe might have collapsed under its own gravity, creating conditions similar to what we think of as the Big Bang, only to rebound into expansion once again. If black holes existed in that earlier phase, the most stable among them could have passed through the transition. When our universe began, they would have been there already, ancient guests in a newborn cosmos. It's a mind-bending thought because it challenges the absolute finality of the Big Bang. We're accustomed to thinking of it as the ultimate beginning, the first page of the cosmic book. But primordial black holes that predate the Big Bang would suggest that the book has earlier chapters we haven't read yet. They would hint at a universe, or many universes, before ours, and that we're living in a story much older and stranger than we ever imagined. And here's where it becomes even more fascinating. If these black holes did survive from a prior cosmic era, then studying them could give us actual physical evidence of what that earlier universe was like. They would not only be fossils from before stars and galaxies, they would be fossils from before our universe itself. That makes them arguably the most valuable objects in the entire cosmos, because they would carry secrets that nothing else could possibly reveal. Of course, this idea is highly speculative. We don't yet have a clear way to test whether any primordial black holes truly existed before the Big Bang. But even the fact that it's possible within certain theoretical frameworks shows how flexible our understanding of the cosmos needs to be. The pre-Big Bang primordial black hole idea is not just about exotic black holes, it's about questioning the very foundations of what we think the beginning means. What makes the idea of primordial black holes existing before the Big Bang so radical is that it directly challenges one of the most foundational assumptions in modern cosmology: the belief that the Big Bang was the ultimate beginning. For decades, the standard cosmological model has painted a clear picture. The universe began 13.8 billion years ago in a hot, dense state and has been expanding ever since. In that story, there is no before. Time, space, matter, and energy all come into existence at that moment. Asking what happened before the Big Bang, according to this framework, is like asking what's north of the North Pole. It doesn't even make sense within the rules. But primordial black holes suggest otherwise. If they truly existed before the Big Bang, then the Big Bang was not the beginning. It was an event within a much larger and older story. Suddenly, the neat narrative of everything started here begins to unravel. The Big Bang, instead of being the cosmic birth, could have been a rebirth, a transformation, or a passage from an earlier state of reality into the one we know now. And that's a paradigm shift so massive that it forces us to rethink not only the origin of the universe but also the nature of time itself. Think about how revolutionary this is compared to the worldview most people hold. The Big Bang has long been the scientific anchor for cosmology. It explains the expansion of galaxies, the abundance of light elements, and the glow of the cosmic microwave background. It's the closest thing we have to a scientific creation story. But if primordial black holes hint at something before, then our creation story isn't complete. It's only the middle of a much longer epic. This is why the idea is so unsettling to some scientists. It doesn't just add a new detail to cosmology, it fundamentally questions the framework. It suggests the possibility of a prehistory of the cosmos, an age before time as we measure it, and relics that survived across what was thought to be an absolute boundary. If that's true, then everything we think we know about beginnings and endings may need to be rewritten. It's also radical because it touches on deeper philosophical questions. For centuries, human beings have asked whether the universe had a beginning or whether it has always existed in some form. The Big Bang was seen as science finally answering that question. Yes, there was a beginning. But primordial black holes throw that answer into doubt. If they are fossils from before the Big Bang, then maybe the universe is eternal after all, cycling through phases of expansion and collapse, or perhaps bubbling up out of some deeper quantum reality. And it's not just philosophy, it's physics. If black holes could survive from one cosmic era to another, then they might carry with them information that the Big Bang did not erase. That means they could be the only objects in existence that bridge two universes. Nothing else, no stars, no galaxies, not even atoms, could have survived the transition. Only black holes, with their extreme resilience, might persist. That makes them not just anomalies but potential keys to unlocking pre-Big Bang physics. This kind of thinking also clashes with the way cosmology is usually done. The Big Bang theory has been successful precisely because it fits the evidence we can observe today. Galaxies moving apart, the microwave background radiation, the abundance of helium. But primordial black holes are difficult to prove or disprove, and their existence before the Big Bang is even harder to test. So suggesting them as relics from a pre-Big Bang universe moves cosmology into territory that many scientists are wary of, territory where evidence is scarce and speculation is bold. It stretches the boundary between testable science and theoretical imagination. And yet, science has always advanced by challenging its deepest assumptions. When Copernicus suggested the Earth wasn't the center of the cosmos, it seemed unthinkable. When Einstein showed that time and space were not fixed but relative, it appended centuries of physics. The idea that the Big Bang might not be the beginning is similarly transformative. It doesn't mean the Big Bang Theory is wrong. It's incredibly successful at describing what happened after the universe began expanding. But it does mean that what we thought of as the ultimate beginning may just be one part of a larger, stranger story. So the radical nature of primordial black holes is not simply that they might exist. It's that they might exist in such a way that forces us to question whether the beginning was truly the beginning. They tug at the edges of our cosmological story, whispering that there may have been something before, that the universe's history might be deeper, older, and more mysterious than we ever dared imagine. To really understand how primordial black holes could have formed in the first place, we have to zoom into the very fabric of reality during the earliest instants of the universe. This takes us into the strange and fascinating realm of quantum fluctuations. In our everyday lives, the world seems stable and predictable. You put a book on a table, and it stays there, solid and unmoving. But at the quantum level, things are never perfectly still. Tiny, random fluctuations constantly ripple through space, like restless waves in an invisible ocean. This jitter is built into the universe itself. Now, right after the Big Bang, the universe was unimaginably dense and hot. Space-time itself was stretched and warped in ways that are difficult even to picture. During this period, known as inflation, the universe expanded at an exponential rate, doubling in size again and again in less than the blink of an eye. Inflation didn't smooth everything out perfectly. Instead, it amplified tiny quantum fluctuations into larger density differences. These weren't just minor bumps. In certain regions, matter could become just slightly more concentrated than in others. And in the extreme environment of the early universe, those slight overdensities could make all the difference. Imagine the universe at that time like a thick soup boiling on a stove. Tiny bubbles appear randomly, some larger than others. Now, instead of soup, picture a sea of energy and matter where some regions were just a bit denser, just a bit heavier. In most places, those fluctuations would stretch out and eventually become the seeds of galaxies and clusters billions of years later. But in a few extreme cases, if a patch of space was dense enough, gravity could have taken over right away, collapsing it into a black hole. These black holes, born not from stars but from the quantum fabric of the early cosmos, are what we call primordial black holes. It's astonishing to think about, because these black holes wouldn't have needed stars or any complicated process to form. They could have popped into existence almost instantly, forged directly from the chaos of quantum fluctuations. What makes this idea so compelling is that it connects two very different scales of physics, the tiniest realm of quantum mechanics and the largest realm of cosmology. Usually, these two worlds don't talk to each other easily. Quantum mechanics describes particles, atoms, and the subatomic world. Cosmology describes galaxies, black holes, and the expansion of the universe. But primordial black holes are the bridge between the two, forming when the tiny fluctuations of quantum physics are blown up by cosmic inflation into structures that reshape the entire universe. The strength of this idea lies in its elegance. We already know that quantum fluctuations were essential to the formation of cosmic structure. The galaxies we see today, the grand spirals and clusters, owe their existence to tiny irregularities in the early universe. Without those fluctuations, everything would have been spread out evenly, and gravity would never have had the chance to clump matter together into stars and galaxies. The fact that we exist at all is proof that quantum fluctuations left their fingerprints on the universe. So the leap to say that some of those fluctuations could have been so extreme that they created black holes isn't as far-fetched as it first sounds. But what's especially fascinating is how wide the possibilities are for these primordial black holes. Because quantum fluctuations happen at every scale, the black holes they produce could span an incredible range of sizes. Some could be tiny, no bigger than an atom, yet still unimaginably heavy. Others could be massive, with weights rivaling thousands of suns. It all depended on the scale of the fluctuation and the moment it occurred during the early universe's expansion. This means that if primordial black holes exist, they wouldn't come in just one size. They would represent a vast spectrum of possibilities, unlike anything we see with stellar black holes. There's another layer of intrigue here. Quantum fluctuations are random by nature. That means primordial black holes, if they formed, could have been scattered unpredictably throughout the cosmos. They wouldn't have needed to follow neat patterns or alignments. Some might be solitary wanderers, drifting invisibly through galaxies. Others might cluster together, hidden in the outskirts of cosmic structures. This randomness makes them harder to detect, but it also means they could explain certain mysteries, like why dark matter appears to be spread so evenly yet invisibly across the universe. When scientists talk about primordial black holes as fossils of the early universe, this is what they mean. They would be the direct products of quantum fluctuations magnified by cosmic inflation. If we could find them, we would essentially be looking at objects that preserve the raw physics of the universe's infancy. They'd be like snapshots of the universe frozen in time, proof that the smallest ripples in reality can create the most massive, enduring structures imaginable. In this sense, primordial black holes aren't just exotic theoretical objects. They're a natural extension of what we already know about the universe, that the tiniest quantum jitters shaped the grandest cosmic patterns. The possibility that those jitters could have gone one step further, collapsing into black holes right at the dawn of time, shows how profoundly interconnected the micro and macro levels of reality truly are. It's a reminder that the universe itself is built from the marriage of randomness and gravity, of quantum chance and cosmic inevitability. One of the most extraordinary features of primordial black holes is the sheer diversity of sizes they could take. When most people think of black holes, they imagine something massive, an invisible giant lurking in space, swallowing stars, or anchoring galaxies. That's certainly true for many black holes we've discovered, but primordial black holes break that mold entirely. Because they didn't form from collapsing stars but from the chaotic density fluctuations in the early universe, their sizes could range across a mind-boggling spectrum, from the microscopic to the galactic. At the smallest extreme, a primordial black hole could be no larger than an atom. Imagine that for a moment, something that tiny, yet still a black hole with an event horizon and all the gravitational power that comes with it. Of course, size in black holes doesn't translate directly to mass in the way we might think. A black hole the size of an atom could still weigh as much as a mountain, billions of tons compressed into a region so small you couldn't see it with the naked eye. This is the kind of scale that makes primordial black holes so bizarre. They could be hiding everywhere, too small to detect directly, yet each one carrying an enormous gravitational influence. On the other end of the spectrum, primordial black holes could be absolutely enormous. Some theories suggest they could be as massive as thousands, or even millions, of suns. These would be titans, rivaling the supermassive black holes we see in the centers of galaxies. The difference is that supermassive black holes grew over billions of years, feeding on gas, stars, and mergers. Primordial black holes of similar mass could have existed right from the start, born in an instant during the first flickers of cosmic expansion. If such giants did exist, they might have played a role in shaping the very structure of the universe, possibly even acting as seeds around which galaxies later formed. Between these extremes lies an almost unlimited variety of possibilities. Some primordial black holes could weigh only as much as an asteroid. Others might weigh as much as Earth or Jupiter. Still others might sit somewhere between the sizes of stellar black holes and supermassive ones. This variety is what makes primordial black holes such a flexible and intriguing candidate for dark matter. Because they could, in theory, exist at all scales, it's possible they fill in gaps in the universe's missing mass across multiple ranges. They could be hiding in plain sight, their effects spread out across the cosmos in ways we haven't fully recognized yet. To get a sense of just how strange these size ranges are, let's compare a few examples. A stellar black hole, formed from a collapsing star, might be 10 times the mass of the Sun and only about 30 kilometers wide. That's already incredibly dense. But a primordial black hole the size of an atom, with the mass of a mountain, would be far denser still, far beyond anything we encounter in ordinary astrophysics. Then imagine a primordial black hole weighing thousands of suns but formed before any stars even existed. It's almost like something out of science fiction, yet it's a real possibility emerging from the mathematics of early universe physics. What's also fascinating is how the size of a primordial black hole determines its fate. Tiny ones, smaller than a certain threshold, would evaporate over time due to Hawking radiation, eventually disappearing in flashes of high-energy particles. Larger ones, however, could survive indefinitely, persisting across billions of years. That means some primordial black holes might have winked out of existence long ago, leaving behind only radiation as evidence of their past. Others might still be out there, as ancient and unchanging as the universe itself. And here's the thing, because of their possible small sizes, primordial black holes could be practically invisible to us. A stellar mass black hole is detectable because of its gravitational effects on nearby stars or gas, or because it emits X-rays when feeding. But a primordial black hole the mass of a mountain would have no such telltale signs. It could drift silently through the galaxy, undetected, unless it happened to pass in front of a background star and reveal itself through gravitational lensing. That makes them ghostly presences, everywhere and nowhere at once. The potential size diversity of primordial black holes also makes them unique compared to other black holes. Stellar black holes have a fairly narrow range, a few to dozens of solar masses. Supermassive black holes are millions or billions of solar masses. There's not much in between, and there's nothing smaller than a stellar black hole because stars set the minimum size. Primordial black holes, by contrast, break those limits. They could exist at every scale, filling the gaps that normal astrophysics cannot. This extraordinary flexibility is one of the reasons primordial black holes are so compelling. They're not constrained by the rules that govern stars and galaxies. Instead, they reflect the wild physics of the early universe, where anything was possible, where density fluctuations could create objects across an unimaginable range of masses. In a sense, primordial black holes embody the creativity of the cosmos itself, able to take any form, from the subatomic to the supermassive, depending on the quirks of quantum fluctuations and inflation. And if they do exist, their range of sizes means they could play many different roles in the universe. The tiny ones might explain certain high-energy phenomena. The medium-sized ones could account for at least part of the mysterious dark matter. The largest ones might have acted as the gravitational anchors that allowed galaxies to form. In every case, their potential variety makes them not just oddities, but central players in the cosmic story. One of the greatest mysteries in all of cosmology is the problem of dark matter. For nearly a century, astronomers have noticed that galaxies simply don't behave the way they should if the only matter inside them were the stars, planets, gas, and dust we can actually see. The edges of galaxies spin far too fast. Galaxies within clusters move as if there's far more gravity pulling on them than what's visible, and even the bending of light from distant objects, the gravitational lensing effect, shows that some kind of hidden mass must be shaping the universe. That hidden mass is what scientists call dark matter, and it makes up about 85% of all the matter in existence. Yet, despite decades of effort, no one has ever detected a single particle of it directly. This is where primordial black holes step in as a fascinating possibility. If they exist in the right numbers and the right sizes, they could be the long-sought answer to the dark matter mystery. Instead of being made of exotic particles that have never been observed, like WIMPs or actions, perhaps dark matter is simply made up of countless primordial black holes quietly lurking in the cosmos. They wouldn't shine, they wouldn't emit light, they wouldn't interact electromagnetically at all, just like dark matter. But they would exert gravity, and gravity is exactly what we see when we study the hidden influence of dark matter on galaxies and the large-scale structure of the universe. The beauty of this hypothesis lies in its simplicity. Black holes are not exotic in the sense of requiring entirely new physics to exist. We already know they can form. We already know how they behave. The only twist is suggesting that a special kind of black hole, born in the early universe, could be numerous enough to account for the mysterious missing mass. This makes primordial black holes one of the most elegant candidates for dark matter, because they don't require us to invent entirely new particles that haven't been observed. They take an already well-understood phenomenon and extend it into a new context. Of course, the picture isn't so straightforward. For primordial black holes to account for dark matter, they would need to exist in specific mass ranges and densities. If they were all extremely tiny, many of them would have evaporated by now due to Hawking radiation, meaning they couldn't account for the majority of dark matter today. If they were all very large, like thousands of solar masses, their gravitational effects on galaxies and cosmic structure would be too obvious. We'd already have detected them. That leaves a sweet spot, a middle ground, where primordial black holes could exist in. Just the right numbers to explain the dark matter problem without contradicting what we observe in the cosmos. This sweet spot has been the subject of intense research. For example, primordial black holes with masses somewhere between that of an asteroid and a few times the mass of the Sun are particularly interesting. They're small enough to have escaped easy detection but large enough to survive until today without evaporating. If billions upon billions of such objects exist scattered throughout galaxies, they could provide the extra gravitational pull needed to explain galactic rotation curves, galaxy cluster dynamics, and the way the cosmic web of matter has evolved. Some astronomers even suggest that the mergers of black holes detected by LIGO and Virgo might be hinting at primordial origins. The black holes observed in those mergers are often about 30 solar masses each, slightly unusual for stellar black holes but consistent with the idea of primordial ones. If these mergers are not just random events but part of a larger population, then perhaps what LIGO is hearing are the whispers of dark matter itself colliding and announcing its presence through gravitational waves. There are also tantalizing connections between primordial black holes and other cosmic mysteries. For instance, if a portion of dark matter is made up of primordial black holes, they could help explain why supermassive black holes formed so early in the universe. Observations show that enormous black holes, billions of times the mass of the Sun, already existed less than a billion years after the Big Bang. That's hard to explain if they had to grow slowly from stars and mergers alone. But if primordial black holes were already around in the right places, acting as seeds, then these supermassive giants could have formed much more quickly. Still, it's important to recognize that not all scientists are convinced. While primordial black holes are an elegant solution, they're not without challenges. Observations of the cosmic microwave background, microlensing surveys, and gravitational wave events all set limits on how many primordial black holes of different sizes can exist. These constraints narrow the ranges where primordial black holes could make up all of dark matter. Some studies suggest they might only be able to contribute part of it, while others leave the door open for them being the entire answer. The debate is far from settled, but what makes this possibility so exciting is that it's testable. Unlike dark matter particle candidates, which have eluded direct detection for decades despite increasingly sensitive experiments, primordial black holes leave signatures in the universe that we can search for. Whether through microlensing events, gravitational wave mergers, or subtle effects on the cosmic background radiation, they give us real pathways to potentially confirm or rule out the hypothesis. And if it turns out to be true, the implications are staggering. It would mean that the solution to the greatest cosmic mystery of our time, dark matter, was hiding in plain sight all along, written into the fabric of the universe since its very first instance. It would mean that what we call dark matter is not some exotic, invisible particle but a population of ancient, hidden black holes, cosmic relics that have been silently shaping galaxies and cosmic structure for billions of years. In other words, the ghosts haunting the universe would be primordial black holes themselves. If primordial black holes really are out there, finding them is no easy task. Unlike stars, they don't shine. Unlike gas clouds, they don't glow in radio or infrared light. Unlike galaxies, they don't leave sprawling clusters of luminous matter behind. A primordial black hole, especially one on the smaller end of the spectrum, could drift silently through the galaxy for billions of years and we would never know, unless it betrayed its presence through some subtle gravitational or energetic effect. That's why when scientists talk about searching for primordial black holes, they almost always mean indirect evidence. They don't expect to see the black holes themselves, but rather the shadows they cast on the universe around them. One of the most straightforward methods is to look for their gravitational influence. Every object with mass bends space-time, and black holes are no exception. If a primordial black hole passes in front of a distant star, the star's light can temporarily brighten as the black hole's gravity bends and focuses the light toward us. This phenomenon is called microlensing, and it's one of the key tools scientists use to search for compact, dark objects like black holes. Experiments such as the Macho Project, OGLE, and more recently Gaia, have scoured the sky for microlensing events. Each flash of brightening light is a clue, and by carefully measuring the timing and intensity of these events, astronomers can estimate the mass of the object responsible. If enough of these events line up with what we'd expect from primordial black holes, we might finally start building a case for their existence. But microlensing is only one path. Another approach involves looking at the cosmic microwave background radiation, the faint afterglow of the Big Bang. This ancient light carries a remarkably detailed map of the early universe, and scientists use it like a cosmic fingerprint. If primordial black holes were abundant, especially in certain mass ranges, they would have influenced the way matter clumped together in those first moments. They could also have injected energy into their surroundings through accretion, slightly heating up the gas in the early universe. These effects would leave subtle imprints in the microwave background, detectable as tiny deviations in its temperature and polarization. By analyzing data from satellites like WMAP and Planck, cosmologists have placed strong limits on how many primordial black holes could exist without contradicting what we see in the background radiation. There's also the hunt for high-energy signals. Small primordial black holes, particularly those with masses lower than a mountain, would have evaporated significantly through Hawking radiation over the lifetime of the universe. Some may even have evaporated entirely, ending in dramatic bursts of gamma rays. If such bursts exist, they might be visible to our gamma-ray telescopes as mysterious flashes of energy. Instruments like NASA's Fermi Gamma-Ray Space Telescope have been scanning the skies for just this kind of signal. While no definitive detection has been made, the search continues, and even the lack of evidence helps refine the mass ranges in which primordial black holes might exist. Gravitational wave observatories have also become a surprising tool in this hunt. The LIGO and Virgo collaborations have detected dozens of black hole mergers, and some of these involve black holes in mass ranges that are a little unusual for stellar remnants. If those particular black holes are primordial, then gravitational waves may be giving us our first direct evidence of their population. It's not proof yet, but it's intriguing, especially since future observatories like LISA, which will be sensitive to lower frequency gravitational waves, could dramatically expand our ability to detect these mergers across cosmic history. Another method lies in looking at the large-scale structure of the universe. If primordial black holes made up a significant portion of dark matter, they would subtly affect how galaxies cluster and how cosmic voids form. By comparing large-scale surveys of galaxies with simulations of how the universe should evolve under different assumptions, researchers can search for mismatches that might point toward black holes as the hidden ingredient. Then there are the more unusual, creative searches. Some scientists propose monitoring stars for tiny, regular vibrations that might indicate a primordial black hole has passed through them. Others suggest that streams of stars in our galaxy, like those pulled out of smaller galaxies or clusters, might show gaps caused by invisible black holes disturbing their paths. Every one of these ideas represents a different angle of attack, a way to catch primordial black holes indirectly through the footprints they leave behind. The frustrating yet fascinating part is that none of these methods have yet produced definitive proof. We have constraints, hints, possibilities, but no smoking gun. Still, the absence of detection is just as important as detection itself. Each experiment that fails to find evidence helps narrow down the range of masses and populations where primordial black holes could still be hiding. It's a process of elimination, slowly closing in on the truth. And the search is far from over. With every new generation of telescopes, detectors, and sky surveys, we open fresh windows into the cosmos. The Vera C. Rubin Observatory, for instance, will track the entire sky with unprecedented depth and precision, vastly improving our ability to catch microlensing events. Next-generation gravitational wave detectors will push deeper into space and time. More sensitive gamma-ray instruments could reveal the faint signatures of evaporating black holes. Together, these efforts are bringing us closer to an answer. What makes this quest so compelling is that it's not just about confirming one theory. Hunting for primordial black holes ties directly into some of the deepest mysteries of modern science. Dark matter, the origins of structure, the validity of our cosmological models, even the question of what might have come before the Big Bang. Each clue, each piece of indirect evidence, is like a breadcrumb leading us toward a potentially revolutionary understanding of the universe. When scientists first switched on the LIGO detectors and heard that faint chirp of spacetime ringing in 2015, it wasn't just the confirmation of Einstein's general relativity that made the world take notice. It was the fact that what LIGO had detected was the collision of two black holes, each around 30 times the mass of our Sun, smashing together more than 1 billion light-years away. For decades, astronomers had speculated about black hole mergers, but this was the first time humanity literally listened to one. The event was groundbreaking, and it opened a whole new way of observing the universe, not with light, but with the ripples of gravity itself. Yet among the many implications of that discovery, one of the most tantalizing was the possibility that some of those black holes weren't the corpses of stars at all. They might have been primordial black holes. Here's why that idea is so intriguing. Most stellar black holes we've observed indirectly, through X-ray emissions or gravitational effects in binaries, tend to be in the range of about 5 to maybe 20 solar masses. They're born from massive stars collapsing after they run out of fuel. But the black holes LIGO and Virgo have been detecting through their gravitational wave signals are often heavier, around 30 to even 50 solar masses, sometimes higher. That doesn't match up perfectly with expectations from stellar evolution models. Massive stars that would form such heavy black holes often lose a lot of their mass through stellar winds before collapsing, especially if they're metal-rich stars like those in our galaxy today. So where are all these unusually heavy black holes coming from? This is where primordial black holes enter the conversation. If the black holes detected by LIGO were born in the very early universe, they wouldn't have gone through stellar winds, nuclear fusion, or supernova explosions. They would have formed directly from density fluctuations in the hot, dense plasma after the Big Bang. In that case, their mass distribution could be very different from the limits we expect for stellar black holes. So when LIGO detected those 30 solar mass mergers, some cosmologists raised their eyebrows and asked, are we hearing the echoes of primordial black holes colliding? The gravitational wave signals themselves carry a wealth of information. By analyzing the waveforms, the exact shape of the chirps, scientists can infer not just the masses of the black holes but their spins. And here's another interesting twist. Many of the LIGO-Virgo black holes don't seem to be spinning very fast. That's odd for stellar black holes, because stars are usually rotating when they collapse, and the angular momentum tends to be preserved, leaving the black hole spinning. If these black holes are primordial, however, formed from collapsing density fluctuations rather than spinning stars, then low or even zero spin would make sense. That spin information is one of the subtle fingerprints scientists look at when asking if some mergers could have primordial origins. Of course, this is still highly speculative. There are astrophysical ways to explain heavier black holes too. For example, in environments with very low metallicity, like the first generation of stars after the Big Bang, stellar winds would have been weaker, allowing stars to retain more mass before collapsing. That could produce black holes in the 30 solar mass range. Similarly, black holes can merge repeatedly in dense star clusters, creating progressively heavier ones. These natural astrophysical channels provide alternatives to the primordial black hole explanation, which is why scientists tread carefully before jumping to conclusions. But the statistical patterns are key. If future gravitational wave detections reveal a whole population of black holes clustered around certain masses, or with systematically low spins, that could be the smoking gun. Primordial black holes, being born in the early universe, would follow different distribution rules than stellar remnants. Over time, as LIGO, Virgo, and their future partners like Kagra and the upcoming Einstein Telescope or Cosmic Explorer build a massive catalogue of black hole mergers, we'll be able to compare those distributions in exquisite detail. Then there's the promise of space-based gravitational wave observatories like LISA, the Laser Interferometer Space Antenna, planned for the 2030s. Unlike LIGO, which detects relatively high-frequency signals from smaller black holes, LISA will listen to lower-frequency gravitational waves, ideal for spotting mergers of supermassive black holes or even intermediate mass ones. If primordial black holes exist in those ranges too, LISA could uncover them. And if PBHs contribute significantly to dark matter, then gravitational waves might be one of the best tools to reveal them. Since gravitational waves don't care if an object emits light or not, they simply record its mass, motion, and collisions. Another layer of fascination is the role PBHs could play in the very early merger events. If primordial black holes formed shortly after the Big Bang, they might have clustered together over billions of years, occasionally colliding and merging. Some of the events we detect today could be the products of those ancient mergers. In that case, every chirp LIGO hears might be more than just two objects colliding. It could be a time capsule, carrying echoes from the primordial fabric of the universe itself. The idea that gravitational wave astronomy could solve the dark matter puzzle is exhilarating. Think about it. For decades, we've built detectors underground, searching for exotic particles of dark matter, and found nothing. Yet in just a few years, listening to the sky with gravitational wave observatories has already given us candidates that might be pointing in another direction. Instead of invisible particles, maybe dark matter is made of invisible black holes, and their mergers are announcing themselves to us across the cosmos. But as always in science, skepticism must run hand in hand with excitement. So far, nothing definitively proves that any LIGO or Virgo detection has a primordial origin. The signals are consistent with multiple scenarios, and disentangling those will take time, data, and creativity. Still, with each detection, the case grows stronger that gravitational waves could hold the key. They're not just a new tool in astronomy, they're a new language in which the universe speaks to us, and primordial black holes might be hiding in its grammar. When you gaze at the night sky, every star you see is pouring light across unimaginable distances, arriving at your eyes after traveling for tens, hundreds, even thousands of years. Normally, that light moves in straight lines through the vast emptiness of space. But what if something invisible crosses that path? What if an object so compact, so dense, yet so dark, passes directly between you and a distant star? You wouldn't see the object itself, it wouldn't glow, it wouldn't reflect, but its presence could still betray itself by bending the star's light, acting like a lens in space. This is the essence of microlensing, one of the cleverest tricks astronomers have at their disposal to hunt for primordial black holes. Einstein's general relativity showed us that gravity doesn't just pull on objects, it bends the very geometry of spacetime itself. That means light, which normally moves in straight lines, curves when it passes near a massive object. This bending effect is called gravitational lensing, and it has been observed on cosmic scales, such as when entire galaxies distort the light of more distant galaxies behind them, producing stretched arcs and rings of light in the sky. Microlensing is the same effect, just on a much smaller, more subtle scale. Instead of a galaxy bending another galaxy's light, a single compact object, a black hole, a neutron star, or perhaps a primordial black hole, bends the light of a single star behind it. What makes microlensing fascinating is that it doesn't require the lensing object to shine. It could be totally invisible, like a primordial black hole. All that matters is its mass. When it passes in front of a distant star, the star's brightness appears to change for a short while. The star can temporarily brighten because the black hole's gravity focuses the light toward us, creating a magnification effect. Then, as the black hole moves on, the star dims back to normal. To an observer on Earth, the star appears to wink, not because it has changed, but because something dark and massive briefly distorted its light. Now, why is this important for primordial black holes? If PBHs really make up some fraction of dark matter, then they should be sprinkled throughout our galaxy, wandering silently in its halo. Occasionally, one should pass in front of a star we're observing. By carefully monitoring millions of stars, scientists can catch these rare events. Projects like MACHO, Massive Compact Halo Object, OGLE, Optical Gravitational Lensing Experiment, and more recently, Gaia, have done precisely this, watching the sky for the telltale brightening that reveals an unseen object drifting across our line of sight. The shape and timing of the brightening gives away the mass of the lensing object. For example, a small black hole with the mass of a mountain might cause a brief flicker lasting hours or days. A heavier black hole, say with tens of solar masses, could produce a much longer, smoother brightening event. By cataloging these signals, astronomers can estimate how many dark, compact objects are out there and in what mass ranges. If a significant number of such events are found, it could suggest that primordial black holes make up a substantial fraction of the mysterious dark matter. But the results so far have been mixed. The MACHO project, which monitored millions of stars in the Large Magellanic Cloud in the 1990s, did detect microlensing events, but not enough to explain all the dark matter if PBHs were responsible. The OGLE survey has continued this work with even more precision, detecting dozens of microlensing events each year, some of which could indeed be caused by compact objects. And Gaia, with its ability to track stellar positions and brightness with extraordinary accuracy, promises to revolutionize this search in the coming decade. Every star Gaia observes could, in principle, become a probe for primordial black holes. The beauty of microlensing is that it doesn't depend on theoretical models of black hole behavior. It doesn't care about Hawking radiation or accretion disks or the environment around the black hole. It only depends on gravity, the most universal force in the cosmos. If a primordial black hole is there, it will bend light, no matter what. That makes microlensing one of the cleanest, most direct tests for their existence. Still, there are challenges. Microlensing events are rare, because the alignment between the star, the black hole, and Earth has to be incredibly precise. You have to watch millions upon millions of stars just to catch a few lucky alignments. And even then, not every microlensing event comes from a black hole. Ordinary stars, brown dwarfs, or even planets can cause similar effects. Disentangling those signals takes careful analysis and statistical work. It's like trying to catch a shadow in a hall of mirrors. You need patience, precision, and massive amounts of data. Looking to the future, new observatories promise to transform this field. The Vera C. Rubin Observatory in Chile, with its Legacy Survey of Space and Time (LSST), will scan the entire southern sky over and over again, producing an unprecedented dataset of stellar brightness variations. That will be a goldmine for microlensing studies. If primordial black holes are out there, Rubin might finally catch them in significant numbers. Combine that with Gaia's precise astrometry, and suddenly we'll have both the brightening and the positional shifts of stars during microlensing events, giving us an even clearer fingerprint of the hidden lens. If one day astronomers confirm that a population of black holes detected through microlensing matches what we'd expect from primordial origins, it would be a revelation. We would no longer be speculating about their existence. We would have direct evidence of dark, ancient objects drifting through our galaxy, silent fossils of the cosmos that might predate the stars themselves. And every flicker, every brief wink of starlight would become a messenger from the deep past, whispering, "Here I am. I was born before your universe had galaxies, before it had suns, before it had planets." When we talk about the deepest echoes of the universe, there is nothing more profound than the cosmic microwave background, the faint afterglow of the Big Bang itself. It is often described as the oldest light in the cosmos, released when the universe was just 380,000 years old, a mere infant compared to its current age of 13.8 billion years. Before that moment, the universe was a hot, dense plasma of particles and photons constantly colliding, scattering, and interacting in a chaotic soup. But as the cosmos expanded and cooled, atoms formed, and suddenly light was free to travel across space. That first light still washes over us today, stretched into microwaves by billions of years of expansion. When we point sensitive detectors at the sky, like those aboard the COBE, WMAP, and Planck satellites, we see it, a faint glow, nearly uniform in every direction, but with tiny temperature variations, minuscule ripples that tell the story of the universe's first structure. These ripples in the cosmic microwave background, or CMB, are more than just noise. They're the fossilized fingerprints of the primordial universe, encoded in faint temperature differences measured in millionths of a degree. And buried in those delicate patterns may lie clues to one of the greatest mysteries of all, primordial black holes. If PBHs were abundant in the early universe, their presence could have subtly distorted this cosmic afterglow, leaving behind faint imprints that we can still search for today. How might this happen? One way is through their gravitational influence. If primordial black holes formed shortly after the Big Bang, their concentrated masses would have pulled on nearby matter, altering the distribution of density in the early universe. These local distortions could show up in the CMB as unusual clustering, as slightly exaggerated hot or cold spots in the temperature map. Scientists analyze the CMB with extraordinary precision, looking for deviations from what standard cosmology predicts. Even the tiniest anomalies can hint at something exotic. Another possible imprint comes from radiation. Small primordial black holes, especially those with masses far below that of the Sun, would slowly evaporate over cosmic time through Hawking radiation, releasing particles and energy. If enough of them existed, their collective evaporation in the early universe could have injected extra energy into the plasma before recombination. That additional heating would change the ionization history of the universe and, in turn, alter the pattern of the CMB. The fact that our current measurements of the CMB are so exquisitely precise, Planck measured temperature differences down to 1 part in 100,000, means we can test whether such scenarios are consistent with what we see. Scientists have also considered how PBHs might affect the damping tail of the CMB. This is the part of the spectrum that reflects how small-scale fluctuations in the early universe got smoothed out by photon diffusion. If PBHs were present, especially in certain mass ranges, they could have introduced additional distortions in these small scales. By comparing theoretical models of PBH populations with the observed CMB power spectrum, researchers can set limits on how many primordial black holes could exist without conflicting with the data. So far, the CMB has placed some of the most stringent constraints on PBHs, especially in lower mass ranges. But the story doesn't end with the CMB's temperature map. There's also its polarization, the way the microwave light is oriented as it reaches us. Polarization patterns carry even more delicate information about the early universe. If PBHs influenced the ionization history or gravitational potential wells in which light traveled, those effects could subtly alter polarization signatures as well. Scientists are now combing through polarization data with hopes of teasing out these faint whispers of PBHs. It's worth pausing to reflect on the scale of this detective work. We are talking about looking at light that has traveled across 13.8 billion years of cosmic expansion, analyzing its tiny fluctuations to ask whether invisible black holes, potentially born before stars, left their shadows on it. It's like listening to a whisper carried across the vastness of time, searching for an accent that reveals who first spoke it. And what makes this especially powerful is that the CMB covers the whole sky. Unlike gravitational wave detections or microlensing events, which rely on rare, specific occurrences, the CMB is universal. Every primordial black hole that ever existed, in principle, contributed to the history it encodes. That means the CMB offers not just a local test, but a global one, encompassing the full cosmic stage. Of course, this doesn't mean PBHs have been confirmed in the CMB yet. On the contrary, much of the research has been about ruling things out, placing upper limits on how many primordial black holes could exist in different mass ranges. For example, too many small PBHs evaporating early on would have completely disrupted the delicate balance of the plasma, leaving clear distortions in the CMB. The fact that we don't see such dramatic distortions tells us they can't dominate the universe in those mass ranges. But that still leaves room for them in other ranges, especially at intermediate or larger masses. Future missions promise to push this even further. Projects like CMB-S4, a next-generation observatory designed to measure the CMB with unprecedented precision, could detect even fainter signals. If PBHs are out there in significant numbers, CMB-S4 might be the tool that finally uncovers their imprints. Combined with gravitational wave astronomy and microlensing surveys, the CMB gives us a complementary way to piece together the puzzle. So, every time scientists produce a new, sharper map of the cosmic microwave background, they're not just mapping the echoes of the Big Bang, they're also, in a way, searching for the shadows of black holes that might predate stars, galaxies, and even our very concept of the beginning. If those shadows are there, hidden in the faint static of the universe's oldest light, then the CMB may yet reveal that primordial black holes were not only real, but deeply woven into the story of creation itself. One of the strangest and most fascinating aspects of black hole physics is that black holes, which we usually think of as eternal prisons from which nothing can escape, might not be completely black after all. In the 1970s, Stephen Hawking made a revolutionary discovery that shook the foundations of physics. Black holes can slowly leak energy through a quantum process now known as Hawking radiation. This insight changed the way we see black holes, turning them from permanent cosmic sinkholes into objects with lifespans, capable of evaporating away over vast stretches of time. To understand this, imagine the vacuum of space not as a perfect emptiness, but as a seething quantum froth. According to quantum field theory, even empty space is full of fleeting pairs of particles and antiparticles popping in and out of existence. Normally, these pairs annihilate each other instantly, leaving no trace. But near the edge of a black hole, the event horizon, gravity is so extreme that it can tear these pairs apart. One particle may fall into the black hole while the other escapes into space. To a distant observer, it looks as though the black hole has emitted a particle. Over time, this slow leakage of energy reduces the black hole's mass, like a cosmic hourglass ticking away at an almost unimaginable pace. For stellar mass black holes, the kind formed by collapsing stars, this evaporation process is laughably slow. A black hole with a mass equal to our Sun would take on the order of 10 years to evaporate, far longer than the current age of the universe. But primordial black holes, which could be much smaller, tell a very different story. If a PBH formed with a mass less than about 1 billion tons, a tiny fraction of a mountain's weight, it would have already evaporated completely by now, because Hawking radiation accelerates as the black hole shrinks. In its final moments, it would unleash a furious burst of radiation, including high-energy gamma rays. This leads to one of the most tantalizing ideas in the search for PBHs. Maybe some of them have already evaporated, and the universe has recorded their final death cries. Astrophysicists have long hunted for sudden bursts of gamma rays, the kind of signal that could represent a tiny primordial black hole disappearing in a flash. Space-based telescopes like NASA's Fermi Gamma Ray Space Telescope and earlier instruments such as EGRET have scanned the sky for these mysterious signals. So far, nothing conclusive has been found, but the absence of detections is itself meaningful. It allows scientists to place limits on how many PBHs of certain masses could exist, since too many would have left an unmistakable gamma-ray signature in our sky. But the search doesn't stop at individual explosions. If a whole population of small PBHs once existed, their slow evaporation over billions of years would have contributed a steady drizzle of radiation into the universe. This could appear as a diffuse background of gamma rays that we can measure today. By comparing observed gamma-ray backgrounds with theoretical predictions, scientists can test whether evaporating PBHs are lurking in the shadows. Once again, so far, the constraints suggest they cannot dominate the universe in the smallest mass ranges, but the possibility of a smaller, hidden population is still open. The idea of PBH evaporation also opens profound theoretical doors. For one, it connects black hole physics with quantum mechanics in a way that forces us to rethink the very fabric of reality. A black hole evaporating means information that once fell inside might somehow be released back into the universe, raising deep questions about whether information can ever truly be lost. This is tied directly to the famous black hole information paradox, one of the great unsolved mysteries in modern physics. If primordial black holes evaporated long ago, their final outbursts may have carried with them subtle clues about how nature resolves this paradox, clues we might one day decipher if we detect the right kind of radiation. There's also a speculative yet intriguing idea: evaporating PBHs might even have influenced the history of life itself. Some physicists have suggested that their bursts of high-energy radiation could have acted as cosmic triggers, possibly influencing star formation, planetary atmospheres, or even biological evolution on Earth. While these ideas remain speculative, they show just how far-reaching the consequences of PBHs could be if they truly existed in abundance. As technology improves, our chances of catching these signals increase. Future gamma-ray observatories, more sensitive and with wider fields of view, may one day detect the telltale flare of a dying primordial black hole. Imagine the significance of such a discovery: a single flash of light, lasting less than a second, yet carrying with it the story of a black hole born in the first fractions of a second after the Big Bang, living quietly for billions of years, and then vanishing before our very eyes. If we ever detect such a signal, it would be like listening to the universe itself whisper across eons, "I was there at the beginning." Primordial black holes, through their evaporation, could leave behind the most dramatic and final proof of their existence. Not just shadows on starlight or imprints on the cosmic background, but a bright, undeniable death cry etched into the cosmos in pure energy. In the Grand Museum of the Cosmos, there are objects that act like fossils, remnants from an ancient time, preserved in forms that tell us stories about origins we could never otherwise witness. On Earth, fossils are bones and imprints of long-dead creatures, silent witnesses to the history of life. In the universe, primordial black holes may be the closest thing we have to cosmic fossils. They are not fossils made of stone or bone, but fossils of gravity itself, potential relics from a time before stars, before galaxies, even before atoms had a chance to gather into the familiar structures we see today. To appreciate this idea, consider the fact that nearly everything in the universe we see around us, stars burning, galaxies swirling, planets forming, is the product of processes that took time. After the Big Bang, matter had to cool, atoms had to form, clouds had to collapse, stars had to ignite, and only then could black holes appear through the deaths of those stars. But primordial black holes break this timeline. If they exist, they predate all of that. They could have formed in the earliest fractions of a second of cosmic history, when conditions were so extreme that matter and energy fluctuated violently, and the tiniest irregularities could collapse under their own gravity into dense singularities. This makes PBHs different from any other objects in the universe. Stars have life cycles, galaxies evolve, planets erode and change, but PBHs are frozen time capsules, locked in their state from the very birth of the cosmos. If we find one, we are essentially touching a fragment of the universe's most primitive moment, a direct physical link to the conditions that existed before even the first atoms had cooled from the primordial fireball. They would embody a chapter of cosmic history that is otherwise completely invisible to us. The fossil analogy becomes even more powerful when you think about how we study the ancient universe. Most of what we know about the early cosmos comes from indirect evidence, like the cosmic microwave background, which captures a snapshot of conditions when the universe was hundreds of thousands of years old. But PBHs, if they exist, are even older. They would be relics not of the baby universe, but of the newborn universe, objects formed in the first split seconds after the Big Bang, still persisting billions of years later. In this sense, they could be more ancient than any other structure in existence. And just as fossils on Earth tell us not only about individual creatures but also about entire ecosystems and environments, PBHs could tell us about the environment of the early universe. Their abundance, or lack thereof, could reveal how matter and energy behaved at densities and temperatures far beyond anything we can reproduce in laboratories. They could expose whether quantum fluctuations were strong enough to seed structures, whether inflation left behind pockets of extreme density, or whether unknown physics operated at the dawn of time. What makes them even more fascinating is the possibility that PBHs, as fossils, are not passive artifacts but active participants in shaping the universe we know. If they were scattered throughout space in the early cosmos, their gravity could have influenced how matter later clumped together, perhaps acting as the scaffolding on which galaxies formed. In this sense, they would be both fossils and architects, ancient relics that helped build the very structures we live in today. This dual role, relic and shaper, is what makes the study of PBHs so compelling. Imagine if paleontologists discovered fossils that were not only remains of ancient creatures but also tools that helped shape the landscape we live on. PBHs may be precisely that, fossils of creation that also engineered the cosmic architecture. The fossil analogy also hints at why they are so difficult to detect. Just as Earth's oldest fossils are rare and fragile, requiring painstaking excavation, PBHs are subtle, invisible except through the indirect clues they leave behind: microlensing events, gravitational waves, gamma-ray signatures, or distortions in cosmic background radiation. Scientists, in a sense, are cosmic archaeologists, sifting through layers of data to uncover traces of these ancient objects. If we confirm PBHs, the implications would ripple through every corner of cosmology. They would show that our universe carries within it relics older than galaxies, older than stars, older than light itself. They would reveal that not everything was wiped away or reset by the Big Bang, that some entities survived, carrying forward information from that primordial moment into the present. They would, in effect, prove that the universe has a memory far deeper than we once thought. And perhaps the most profound aspect of viewing PBHs as cosmic fossils is what it says about time. Fossils on Earth remind us that the present is not isolated, but the latest chapter in a long story of transformation. PBHs would do the same, but on a cosmic scale, telling us that the universe is not simply an unfolding from a singular beginning, but a continuum where the past still lingers, silently orbiting among the stars. They would whisper to us that the universe is both ancient and alive, that its earliest moments are not lost but preserved in the most unlikely of places: black holes, tiny or massive, scattered across the void. In that sense, primordial black holes would not just be fossils of the universe's first moments, they would be fossils of mystery itself, preserved evidence that something unimaginably powerful and strange happened at the dawn of creation, something that still shapes us today. When we say the phrase "before the Big Bang," it sounds almost paradoxical, as though we're trying to describe something that shouldn't exist. According to the traditional view of cosmology, the Big Bang wasn't just the birth of all matter and energy, it was also the birth of time itself. If time began at the Big Bang, then asking what came before might seem like asking what's north of the North Pole. Yet human curiosity and scientific imagination have never been content with simply saying, "there was nothing." Over the past few decades, physicists and cosmologists have proposed a variety of bold theories that stretch beyond the Big Bang and attempt to define what before could mean. One interpretation comes from the idea of cosmic cycles. In this picture, the Big Bang was not the beginning of everything, but rather the latest event in an endless sequence of cosmic expansions and contractions. Just as a beating heart contracts and expands rhythmically, the universe itself may breathe in cycles, collapsing into a big crunch, then rebounding in a new Big Bang. If this is true, primordial black holes could serve as the ultimate survivors, enduring through the collapse of one universe and reappearing in the next. They would carry with them information from earlier cycles, literal fossils not just from one universe, but from many. This idea, known as cyclic cosmology, suggests that the story of the cosmos might be eternal, with no true beginning or end, only recurring chapters. Another line of thought comes from quantum gravity, which tries to merge Einstein's general relativity with quantum mechanics. One of the most intriguing proposals from this area is the quantum bounce idea. Instead of a singularity where all the laws of physics break down, the universe may have reached a point of maximum compression and then bounced outward. Imagine compressing a spring. There's a limit to how far it can be squeezed before it snaps back. In a similar way, the universe could have existed in a contracting state before the Big Bang, and the explosion we call the Big Bang was actually the rebound of that process. In such a model, black holes from the contracting phase could potentially survive the bounce, meaning primordial black holes might be relics not of our universe's beginning, but of an earlier one that came before. There is also the possibility of an earlier universe in a more literal sense. Some theories in string cosmology, for instance, describe a multiverse or a pre-existing state from which our universe emerged. The Big Bang, in this view, wasn't the creation of everything, but a transition, a dramatic phase change in a larger reality. It's similar to how water can boil and turn into steam. The steam wasn't created from nothing, it was simply transformed from another state of matter. If the Big Bang was such a transformation, then PBHs could be remnants of the previous phase, fossils from a universe that once existed before ours. Each of these possibilities, cycles, bounces, and earlier universes, changes the meaning of before in subtle but important ways. Before might mean a time in a prior cycle, it might mean a different state of existence that preceded our expansion, or it might mean another universe altogether, existing in a grander multiversal landscape. In all cases, primordial black holes act as a kind of key. Their very existence would imply that something tangible persisted across the supposed boundary of the Big Bang. They would be evidence that the Big Bang was not the ultimate beginning, but a doorway between realities. It's worth emphasizing how radical this is. For decades, the Big Bang has been treated as the definitive origin of everything, a boundary condition where physics as we know it stops. But by entertaining the idea of before, scientists are extending the scope of cosmology beyond the horizon of our own universe's birth. This isn't just theoretical play, it's motivated by real puzzles, like the nature of dark matter, the uniformity of the cosmic background, and the mathematical inconsistencies of singularities. Primordial black holes serve as a test of these bold ideas. If we find them, they could be the missing link between our universe and whatever came before. The very fact that we are asking these questions shows how deeply the idea of before the Big Bang challenges our imagination. Time, causality, and beginnings are so deeply embedded in human thought that stepping outside them feels almost impossible. And yet, the existence of PBHs whispers that maybe the universe has always been older and stranger than our current models suggest. To speak of before is to accept that our cosmic story might not be a single straight line, but part of a vast tapestry that stretches beyond the horizon of what we can see, beyond the moment we call the beginning. The notion of bounce cosmologies takes us into one of the most captivating frontiers of modern physics, a place where the universe isn't a one-time event but part of a grander rhythm. In this view, the Big Bang wasn't a singular beginning but rather a rebound, a bounce from a previous state of contraction. Instead of time and space emerging from nothing, the cosmos has always existed in cycles of expansion and collapse, breathing in and out on unimaginable timescales. This picture doesn't just provide an alternative to the traditional something-from-nothing scenario, it also offers a natural place for primordial black holes to come into play, potentially as survivors from an earlier cosmic epoch. To grasp this, imagine the universe as a vast balloon. In the standard Big Bang picture, the balloon starts at a point and inflates endlessly. But in a bounce cosmology, the balloon isn't brand new, it has already expanded and deflated many times. Each cycle ends in a collapse, a contraction of the universe into an incredibly dense state, followed by a bounce that triggers a new round of expansion. If this is true, then the Big Bang we talk about in textbooks wasn't the first, but simply the most recent bounce in an eternal sequence. In such a model, primordial black holes gain a fascinating new role. During the collapse phase of a previous universe, enormous densities and pressures would have arisen. Regions of spacetime where matter accumulated more heavily could have collapsed into black holes. Normally, one might expect such objects to be destroyed or transformed during the violent crunch and bounce. But black holes are strange in that their defining feature, the event horizon, shields whatever lies within from the external universe. In some theories, This protective boundary could allow them to survive transitions between cycles. If so, then PBHs in our universe might not have formed after the Big Bang at all. They might literally be holdovers from a universe that came before ours. This is part of what makes bounce cosmologies so profound. They not only stretch the lifespan of the universe infinitely backward, but they also suggest continuity across cosmic cycles. Black holes could be the seeds that persist from one universe to the next, carrying forward the gravitational memory of earlier epochs. If some of these black holes were relatively small, say, the mass of a mountain or a planet, they might have survived evaporation, lingering through countless cycles. Larger ones could even act as gravitational anchors, influencing how matter clumps together in each new universe. Several theories try to describe how such bounces might work. In loop quantum cosmology, for example, the mathematics of quantum gravity replaces the singularity of the Big Bang with a bounce. Instead of everything compressing into a dimensionless point, the density reaches a maximum finite value, after which quantum effects cause it to rebound. In this scenario, the contraction phase before our universe might have looked like a mirror image of expansion, and black holes formed during that phase could have endured the transition. Other bounce models come from string theory, where the universe may undergo cycles driven by the dynamics of extra dimensions. In some versions, brands, hypothetical higher dimensional surfaces, collide and separate repeatedly, with each collision resembling a Big Bang. PBHs could easily be created during these violent brain collisions, and if they are stable enough, they could traverse from one cycle to the next. The presence of PBHs in a bounce cosmology isn't just speculation, it has profound observational consequences. If PBHs are relics from earlier cycles, they might exist in populations or distributions that differ from those expected if they formed just after our own Big Bang. By carefully studying gravitational waves, microlensing events, or cosmic background signals, scientists might one day distinguish whether these objects were born in this cycle or inherited from previous ones. Finding PBHs with certain mass ranges or densities could act as evidence that the Big Bang was indeed a bounce, not a beginning. What's astonishing here is that bounce cosmologies allow us to think of the universe not as a fragile one-off miracle, but as something eternal and self-renewing. The cycles of contraction and expansion could have been going on forever, each bounce giving rise to galaxies, stars, and civilizations, only to collapse again and start anew. And through it all, primordial black holes might play the role of cosmic survivors, witnesses to countless universes before ours, timeless fossils carried forward through the tides of creation and destruction. If PBHs are discovered, and if their properties suggest an origin older than our Big Bang, then bounce cosmologies would leap from the realm of speculation to the center of physics. They would tell us that our universe is part of a much older and grander narrative, a story without a true beginning, only endless cycles where black holes persist as the ultimate cosmic constants. String theory brings an entirely different layer of imagination into the conversation about primordial black holes. At its heart, string theory proposes that the most fundamental building blocks of the universe are not point-like particles but tiny vibrating strings of energy. These strings can vibrate in different ways, and their modes of vibration give rise to the particles we observe, like quarks, electrons, and photons. What makes string theory especially relevant here is that it naturally predicts extra dimensions beyond the familiar three of space and one of time. And when cosmologists take these extra dimensions seriously, fascinating scenarios about the early universe, and potentially about black holes that predate the Big Bang, begin to emerge. In some versions of string cosmology, our universe exists as a three-dimensional brain floating in a higher dimensional space. Imagine a sheet of paper suspended in a room. The sheet represents our universe, while the room is the higher dimensional bulk. Within this framework, the Big Bang could be reinterpreted as a collision between brands. Instead of matter and energy spontaneously appearing out of nothing, the fiery birth of our universe might have been the result of two higher dimensional surfaces smashing into each other. Such a collision would release tremendous energy, enough to create the hot, dense plasma that evolved into the universe we see today. Now, where do primordial black holes come into this picture? During these violent brain collisions or in the chaotic high-energy states that string theory allows, density fluctuations on extremely small scales could have formed black holes. Because these processes might predate or go beyond the standard Big Bang timeline, such PBHs would not simply be relics of our universe's infancy, They could be survivors from earlier phases of a multiverse-like landscape. In some scenarios, black holes formed in one cycle of brane collisions could persist and then carry over into the next cycle, surviving the transition into what we call our Big Bang. String cosmology also predicts the possibility of exotic types of black holes, tied to the higher dimensions themselves. For instance, in a universe with additional spatial dimensions, gravity behaves differently at very small scales. This altered gravitational landscape could allow black holes to form much more easily in the early universe than our four-dimensional physics would suggest. Some of these black holes could be microscopic, far smaller than stellar remnants, but still massively dense. If stable, they could still be floating in the cosmos today, invisible but influential, perhaps even making up a portion of dark matter. Another intriguing connection is how string theory's landscape of possible universes, the so-called multiverse, allows for transitions between different phases of reality. The Big Bang might simply represent one such transition, and black holes could act as the rare survivors of these phase changes. Just as certain fossils survive catastrophic extinctions on Earth, primordial black holes might survive cosmic resets or reconfigurations of spacetime itself. This possibility is part of why physicists who work in string cosmology often view PBHs as more than just hypothetical curiosities. They could be tangible traces of pre-Big Bang physics embedded in our universe. What's particularly appealing about string theory in this context is that it ties together phenomena that otherwise seem disconnected. The same framework that seeks to unify gravity with quantum mechanics also provides a natural context for brane collisions, cyclic universes, and black hole relics. Primordial black holes could thus serve as experimental windows into string theory's predictions. If we detect PBHs with certain unusual properties, masses, distributions, or gravitational effects inconsistent with post-Big Bang formation, it might serve as indirect evidence for the validity of string cosmology itself. This brings us to the tantalizing idea that primordial black holes, if discovered, might be more than astrophysical curiosities. They might be the closest thing we have to experimental proof of string theory. While testing string theory directly is notoriously difficult due to the extreme energies involved, PBHs could act as messengers from the realms where string theory operates, conditions of density and energy far beyond what we can reproduce in laboratories. So, in the string theory perspective, PBHs are not just relics of the early universe, they are remnants from deeper cosmic structures, possibly born of higher dimensional physics or violent brane collisions that gave rise to our universe. If we ever confirm their existence, it could mean we are literally holding the fingerprints of string theory in our observations of the sky. These black holes might whisper to us about dimensions we cannot see, about universes that existed before ours, and about the fundamental nature of reality that strings and brands are striving to describe. Loop quantum gravity is one of the boldest attempts to bring quantum mechanics and general relativity together, and it provides a fascinating framework for thinking about primordial black holes. Unlike string theory, which introduces extra dimensions and vibrating strings, loop quantum gravity, LQG, takes a more minimalistic route. It suggests that space and time themselves are not continuous but are instead made of tiny, discrete building blocks, almost like pixels on a cosmic screen. Imagine space-time as a fabric, but zoom in closely enough and you would see it's woven from incredibly small loops of energy. This radical idea changes the way we think about singularities, the places where Einstein's equations usually break down, such as the center of black holes or the instant of the Big Bang. In traditional general relativity, the universe's beginning is a singularity, an infinitely dense point where the laws of physics as we know them stop working. But loop quantum cosmology, which applies LQG principles to the whole universe, replaces that singularity with something different, a bounce. Instead of space and time collapsing into nothingness, the density of the universe reaches a maximum, and then quantum effects cause it to rebound. In this sense, the Big Bang isn't the beginning but rather a transitional event, the turning point between a previous contracting universe and our current expanding one. This perspective has profound implications for primordial black holes. If the universe undergoes bounces rather than singular beginnings, then black holes formed in a contracting phase could survive into the expanding phase. In other words, PBHs could act as passengers riding the transition from one cosmic era to the next. Their event horizons and immense gravitational strength might protect them from being obliterated, even during the most extreme conditions of the bounce. While galaxies, stars, and ordinary matter might be reset or redistributed, PBHs could persist as stable structures bridging one universe to another. Some researchers even suggest that the very properties of loop quantum gravity make PBHs particularly relevant. In LQG, the smallest scales of spacetime have a kind of resistance to infinite collapse. This means that singularities inside black holes might also be avoided, replaced instead with a quantum core that prevents total breakdown. If this is true, then black holes themselves could undergo bounces internally, turning into what some call Planck stars. These are hypothetical objects where the intense gravity of a black hole eventually causes it to explode outward in a kind of quantum rebound. If primordial black holes contain such cores, they might not only survive universal bounces but also act as laboratories for quantum gravity, revealing what happens inside the most extreme objects in the cosmos. From the perspective of loop quantum cosmology, PBHs serve two roles at once, as survivors of past universes and as testbeds for the deepest questions about quantum gravity. They could tell us not only that a universe existed before ours, but also how the fabric of spacetime itself behaves under the most extreme conditions. If observational evidence for PBHs is ever found, whether through gravitational waves, microlensing, or gamma-ray signals, it could provide indirect support for the idea that our universe didn't begin from nothing but emerged from a quantum bounce. The idea is breathtaking in its simplicity. Black holes, the very objects once thought to represent the ultimate dead ends of physics, might instead be the cosmic bridges linking one universe to the next. Primordial black holes surviving across cycles would not just be relics of the past but guardians of continuity, carrying imprints of physics deeper and older than our own cosmic chapter. They would stand as silent witnesses to a universe that has lived, died, and been reborn countless times, their presence offering us the closest thing to proof that time itself may be infinite, and that creation is not a single event but an eternal process. The question of why primordial black holes might survive when so many other structures are destroyed in the chaos of cosmic evolution strikes at the very heart of their mystery. Stars, galaxies, even atoms as we know them, are fragile compared to the cataclysmic forces at play in the early universe. They form, they collapse, they scatter. Yet black holes are different. They are not made of matter in the same way stars or planets are. They are regions of spacetime itself, pure geometry shaped by gravity. That difference may be the key to understanding why PBHs could endure events that would otherwise erase everything else. To see why, let's imagine the early universe again, an ocean of fire and density where ordinary matter had no chance of stability. At that time, even the simplest structures, like protons and neutrons, were being torn apart and reassembled constantly. Galaxies, stars, and planets didn't exist yet. They were still billions of years away. But black holes, if formed then, would not depend on the survival of atoms or molecules. They are not objects in the traditional sense but distortions of spacetime created when matter collapses past a critical density. Once an event horizon forms, it separates the inside from the outside forever, making the black hole self-contained. This event horizon acts like a shield. No matter what happens around the black hole, whether temperatures soar, radiation floods space, or spacetime itself stretches, the contents inside remain hidden, untouched by external forces. In a sense, the black hole detaches itself from the usual rules that govern matter. Even during cosmological transitions as radical as a Big Bang or a bounce, the horizon may stay intact, allowing the black hole to persist. That is why PBHs are sometimes seen as cosmic survivors, entities that might carry with them information from eras long before any stars lit the universe. Another reason PBHs could survive is scale. Unlike stars or galaxies that depend on delicate balances between pressure, gravity, and nuclear fusion, black holes thrive on collapse. They are born out of instability, and once formed, they can remain stable indefinitely unless disturbed by very specific processes, like Hawking radiation for extremely small ones. Larger PBHs, with masses greater than a few billion tons, would evaporate so slowly that even the entire age of the universe isn't enough time for them to disappear. That means if PBHs formed in the first fraction of a second after the Big Bang, many of them could still be here, unscathed by cosmic expansion or galaxy formation. Some theorists even suggest that PBHs may not just survive cosmic catastrophes but might endure the ultimate catastrophe, the collapse of an entire universe. In bounce cosmologies or cyclic models, as the universe contracts, everything becomes denser, hotter, and more chaotic. Galaxies would be shredded, stars obliterated, particles fused into strange states of matter. Yet PBHs, instead of being destroyed, might become part of the very fabric of the crunch. When the bounce occurs, they could pass through into the new cycle, reborn in the expanding phase of a new universe. Their sheer simplicity, the fact that they are defined only by mass, spin, and charge, might be exactly what makes them resilient enough to transcend cosmic death and rebirth. Even if we don't invoke bounces or cycles, PBHs still have a survival advantage in our standard cosmological picture. Unlike other hypothetical dark matter candidates that could decay over time, black holes are stable solutions of Einstein's equations. They don't require exotic new physics to endure. Once they exist, they can only vanish through slow evaporation or by merging with other black holes. In a universe filled with violent processes, this makes them almost indestructible compared to everything else. So when we ask why PBHs could persist while ordinary matter gets erased, the answer lies in their nature. They are not delicate. They are not dependent on temperature, chemistry, or nuclear forces. They are gravity distilled into its purest form, carved into space-time itself. In this way, they might be the closest thing we have to permanent structures in a cosmos otherwise defined by change. If PBHs do survive across vast stretches of time, or even across entire cycles of universes, they could serve as the ultimate cosmic fossils. Their very existence would prove that something can endure the most extreme events imaginable. They would carry, hidden within their horizons, information about the conditions in which they formed. They could be, quite literally, the only witnesses to a time before time as we know it. If we think of primordial black holes not merely as oddities of the early universe but as time capsules, the picture becomes even more astonishing. Unlike stars, planets, or even galaxies, which constantly evolve, change, and decay, PBHs are frozen relics of the exact conditions in which they were born. Every PBH is a snapshot of space-time itself at the moment of its creation, locked away behind an event horizon that preserves its secrets across billions of years. In this way, PBHs could act like sealed containers, holding within them information about physics not just at the dawn of the universe but potentially even before the Big Bang. Consider what a time capsule does. It preserves artifacts from one age so that future generations can uncover them and learn about the past. Primordial black holes, by their very nature, could serve a similar function. Their masses, spins, and distribution across the cosmos may encode details about the density fluctuations, quantum conditions, and physical laws that govern their formation. If PBHs existed before the Big Bang, as some speculative theories suggest, then they could contain imprints of pre-Big Bang physics, making them relics older than time itself as we measure it. How could PBHs preserve such information? The key lies in their resilience. Once a black hole forms, it becomes cut off from the ordinary evolution of matter. Its event horizon isolates the inner region from the external universe, ensuring that the physical state at its core remains hidden but intact. Unlike atoms, which get torn apart in extreme conditions, or galaxies, which dissolve and merge, black holes are fundamentally shielded from external disruption. That isolation makes them unique as potential record keepers of primordial conditions. Some scientists even speculate that PBHs might carry clues about forces of nature that no longer dominate our universe. In the very early cosmos, or in a pre-Big Bang state, fundamental constants might have been different. The strengths of gravity, electromagnetism, or nuclear forces could have varied in ways we cannot observe directly today. If PBHs formed during such exotic phases, their properties may silently reflect those forgotten physical laws. In this sense, each PBH could be an archive of ancient physics, a relic of regimes no longer accessible through experiments or observations. The very distribution of PBHs across the cosmos could itself serve as a kind of record. Imagine that they are not spread randomly but instead cluster in certain ways. Those patterns might mirror the structure of density fluctuations in the early universe or even in a previous contracting universe. By studying where PBHs are, how massive they are, and how they interact, cosmologists might decipher a hidden code, an astronomical archive written in the language of gravity. There's also the tantalizing possibility that PBHs could connect to one of the deepest puzzles in modern physics, the black hole information paradox. According to classical physics, information that falls into a black hole is lost forever, hidden beyond the event horizon. But quantum mechanics insists that information can never truly be destroyed. Reconciling these two ideas has troubled physicists for decades. Now imagine if PBHs, as the oldest black holes in existence, hold within them information not only about what fell into them after they formed, but also about the very moment of their creation. If we could find a way to extract even a hint of that information, perhaps through subtle signatures in Hawking radiation or gravitational wave patterns, it might provide answers to questions that span not just our universe but whatever came before it. This idea reframes PBHs from mere curiosities to profound messengers. They are not just black voids scattered across the cosmos. They are potential archives of forgotten epochs, cosmic safes that hold keys to understanding what reality looked like before the stars, before space itself expanded, perhaps even before the Big Bang lit the fuse of our universe. To study them is to try to open those safes, not with crowbars or dynamite but with the tools of theoretical physics, astronomy, and quantum mechanics. And that raises a hauntingly beautiful possibility. If PBHs really are time capsules, then scattered across the dark expanses of space are countless sealed windows into epochs that we cannot otherwise reach. Every one of them might contain the story of a universe older than our own, waiting silently to be decoded. The black hole information paradox is one of the most profound riddles in modern physics, and primordial black holes might play a surprising role in unraveling it. To understand why, we first need to revisit what this paradox actually means. In simple terms, it arises from a clash between two pillars of science: general relativity, which governs gravity and the large-scale structure of spacetime, and quantum mechanics, which dictates the behavior of particles and information on the smallest scales. Normally, these two frameworks operate in separate domains, but black holes force them into the same arena, and that's where the contradictions begin. In Einstein's general relativity, when something falls into a black hole, it is gone from the universe forever, sealed away behind the event horizon. No light, no particles, no information about what entered can escape. The black hole is characterized only by a few basic properties: its mass, its spin, and its electric charge. Everything else, the shape of the star that collapsed, the arrangement of its atoms, the complex history of the matter, vanishes from the observable universe. This is often summarized in the phrase, "Black holes have no hair." But quantum mechanics refuses to allow such a clean erasure. One of its deepest principles is that information is never destroyed. It may be transformed, scrambled, or hidden, but it always exists in some form. If black holes truly destroy information, then quantum mechanics would break down, and with it the foundation of all modern physics. On the other hand, if quantum mechanics is right and information is preserved, then something about our understanding of black holes must be incomplete. That tension is the information paradox. Stephen Hawking intensified the paradox in the 1970s when he proposed that black holes are not completely black after all. Through what's now called Hawking radiation, black holes should slowly evaporate by emitting particles due to quantum effects near their horizons. Over unimaginable timescales, a black hole could shrink, radiate away all its mass, and eventually vanish. But here's the problem: the radiation seems to be purely thermal, carrying no imprint of the specific information about what fell into the black hole. If the black hole disappears completely, the information would be lost with it, an outcome quantum mechanics says cannot happen. Now bring primordial black holes into the story. Unlike stellar black holes, which are relatively young compared to the universe, PBHs could be as old as the cosmos itself, or even older, if they predate the Big Bang. That longevity makes them unique test cases for the information paradox. If small PBHs have been evaporating over cosmic time, their Hawking radiation might leave detectable signatures, such as bursts of high-energy gamma rays. If those signatures carry subtle imprints of the information they once contained, it could provide the first real clue about whether information is preserved or lost. Detecting such a signal would be revolutionary, suggesting that black holes are not information shredders but rather extreme cosmic computers that eventually release what they absorbed, though in a profoundly scrambled form. Larger PBHs, on the other hand, might not yet have evaporated significantly. If we could find them, they would act like long-lived archives of information stretching back to the earliest epochs. Their very survival could show us how the laws of physics handle continuity across vast scales of time, perhaps hinting at mechanisms that reconcile quantum rules with the gravitational rigidity of black holes. Even their distribution and masses might reflect the way information flowed in the earliest universe, giving us indirect insights into whether the paradox can be resolved by new physics. There are speculative but intriguing theories suggesting that the interiors of black holes might not be annihilated singularities at all, but instead exotic quantum structures, things like Planck stars or holographic encodings of information on their horizons. If this is true, PBHs become more than just relics. They become laboratories for testing the very nature of information itself. The fact that they could span such a wide range of sizes, from tiny evaporating ones to colossal giants, means they offer multiple experimental windows into the problem. Some theorists even propose that PBHs could act like cosmic vaults, preserving pre-Big Bang information within their cores. If that information is not destroyed but stored in some encoded form, then PBHs might hold the key not only to the paradox but also to the history of a universe older than our own. In this sense, solving the paradox through PBHs is not just a matter of fixing a theoretical inconsistency. It is about gaining access to a hidden record of cosmic events otherwise lost forever. So when we look at primordial black holes, we're not just asking whether they exist. We're asking whether they are guardians of one of physics' deepest secrets. If PBHs can help resolve the information paradox, then they are not merely cosmic fossils. They are proof that information, the very fabric of reality, is indestructible, even in the most extreme corners of the universe. When we look out into the night sky and see the countless galaxies spread across the cosmos, each containing billions upon billions of stars, it's easy to forget just how astonishing their existence really is. Galaxies are not just pretty spirals or glowing clusters of light. They are massive, gravitationally bound structures, and their very formation poses deep questions. How did such immense systems emerge so quickly after the Big Bang? Why do galaxies appear where they do? And why do they take on the shapes they take? One tantalizing theory suggests that primordial black holes may have played a central role in this story, acting as the original seeds around which galaxies gathered and grew. To understand why this idea is so compelling, we need to step back to the early universe. After the Big Bang, the cosmos was nearly uniform, filled with a hot plasma of particles. But it wasn't perfectly smooth. Tiny fluctuations, imperfections in the density of matter, existed, and these small irregularities provided the scaffolding for cosmic structure. Over billions of years, gravity amplified them, causing matter to clump together, forming stars, galaxies, and eventually the cosmic web we see today. But here's the problem. Given the smoothness of the early universe, it's hard to explain how galaxies formed as quickly as they did without some extra catalyst, some gravitational anchors that could speed up the process. Primordial black holes fit this role perfectly. If PBHs formed within the first second of the universe's existence, then they would have been present before stars or galaxies ever existed. Their immense gravity would have acted like seeds in a garden, drawing in surrounding gas, dark matter, and later, stars. Around these gravitational wells, larger structures could have formed much faster than they would have by relying solely on the tiny density fluctuations left over from the Big Bang. This idea makes PBHs cosmic gardeners, planting the first seeds from which galaxies sprouted. Imagine a PBH with just the right mass embedded in the early cosmic soup. As the universe expanded and cooled, that PBH would begin to attract matter from its surroundings. Gas would swirl around it, dark matter would clump nearby, and over time, these ingredients would coalesce into something much larger. In essence, the PBH could have served as the anchor for a future galaxy, with its immense pull organizing the chaos of the early universe into coherent structures. Some even suggest that supermassive black holes, the giants we see today at the centers of most galaxies, might actually be descendants of primordial black holes. Instead of forming from the collapse of massive stars, these central monsters may have been PBHs from the very beginning, growing larger over cosmic time as they devoured matter and merged with other black holes. This is not just speculation pulled out of thin air. Observations show that supermassive black holes existed surprisingly early in the universe's history, within just a few 100 million years after the Big Bang. Traditional models of black hole growth struggle to explain how such giants could appear so quickly. Stellar black holes, which form from collapsed stars, would not have had enough time to grow into billion solar mass behemoths so early. But if some PBHs were born massive, they could easily explain the presence of these ancient cosmic giants. They might have acted as the gravitational cores around which entire galaxies assembled. The theory extends beyond just explaining galaxy formation. It also ties into the broader structure of the universe. The large-scale cosmic web, the vast network of filaments, clusters, and voids, might have been shaped by the gravitational influence of PBHs distributed throughout the cosmos. Their presence could help explain why matter gathered the way it did, why some regions became rich with galaxies while others remained barren voids. Of course, this idea is not without challenges. Not all scientists are convinced PBHs are necessary for galaxy formation. Standard cosmology already accounts for structure through dark matter and density fluctuations. But PBHs add an elegant shortcut. They would provide gravitational seeds powerful enough to accelerate the entire process, explaining both the rapid appearance of supermassive black holes and the early formation of galaxies in one stroke. If true, this would radically change how we see galaxies. Instead of being entirely the product of star-driven processes, galaxies would be, at their core, children of primordial black holes. Every time we look at the Milky Way or Andromeda or the billions of galaxies stretched across the sky, we might be looking at vast cosmic gardens that first sprouted around invisible seeds sown before the stars themselves were born. It's a poetic possibility that the galaxies we see as the great cities of the cosmos were founded upon the gravitational bones of ancient PBHs. In this view, our very existence, our sun, our planet, and even life itself, may be traceable back to the unseen seeds planted in those first cosmic instants. Without primordial black holes, the universe might not have grown the way it did, and we might never have come to be here to ponder them. When scientists consider the role of primordial black holes in the cosmos, they're not only thinking about them as possible seeds of galaxies or relics of the early universe, they're also weighing them against other exotic possibilities for one of the greatest mysteries in modern physics: dark matter. Dark matter makes up roughly 85% of all the matter in the universe, yet we've never seen it directly. It doesn't emit light, it doesn't reflect it, and it doesn't interact with ordinary matter in ways we can easily detect. Its existence is inferred only from its gravitational pull, the way it bends light and holds galaxies together. Without dark matter, galaxies would fly apart. Without dark matter, the cosmic web wouldn't exist as we see it. And for decades, scientists have been chasing the identity of this ghostly component of reality. Primordial black holes are one candidate, but they're competing with other fascinating possibilities. The most famous ones are WIMPs, weakly interacting massive particles. For many years, WIMPs were the frontrunners in the race to explain dark matter. The idea is simple. They would be heavy particles that interact with ordinary matter only through gravity and the weak nuclear force, making them nearly impossible to detect. They would have formed naturally in the high-energy furnace of the early universe and then lingered ever since, filling the cosmos invisibly. The beauty of WIMPs is that they arise naturally in many extensions of the standard model of particle physics, especially supersymmetry. For decades, scientists expected that large underground detectors or particle accelerators like the Large Hadron Collider would eventually reveal them. But despite years of searching, no definitive sign of WIMPs has been found. Another exotic candidate is the axion, an almost massless particle originally proposed to solve a problem in quantum chromodynamics, the theory of the strong nuclear force. Axions would interact so weakly with ordinary matter that trillions could be passing through us right now without leaving a trace. They're appealing because they could explain not just dark matter, but also certain puzzles in particle physics. Physicists have built highly sensitive experiments, including powerful radio-like detectors, to listen for the faint whispers of axions converting into photons under magnetic fields. So far, the evidence is elusive. Then there are even stranger proposals: sterile neutrinos, hidden sector particles, fuzzy dark matter made of ultralight bosons, and entirely new forces of physics. Each idea comes with its own theoretical motivations, experimental challenges, and implications for cosmology. Primordial black holes, in contrast, stand out because they're not new particles invented to fill a gap. They're objects we already know can exist, predicted by general relativity itself. If they formed in the early universe, their gravitational effects could account for at least part of the missing dark matter. The advantage here is conceptual elegance. PBHs don't require entirely new physics, just the right initial conditions in the cosmos. They could naturally arise from density fluctuations, inflationary processes, or even earlier pre-Big Bang epochs. Yet PBHs also face challenges. If too many of them existed in certain mass ranges, we would already have seen their effects. Distortions in the cosmic microwave background, unusual gravitational lensing events, or excess radiation from evaporating small black holes. Observational surveys have already ruled out PBHs as the entirety of dark matter across wide ranges of mass. But there are still gaps, windows where PBHs could plausibly make up some or even most of the dark matter, particularly in intermediate mass ranges. This comparison creates an interesting divide in cosmology and physics. On one side, particle physicists search for exotic particles like WIMPs and actions, building ever more sensitive detectors deep underground and in space. On the other side, astrophysicists and cosmologists turn their eyes to the heavens, hunting for the gravitational fingerprints of PBHs across the sky. Both camps are, in a sense, chasing shadows, things we cannot see directly, but which bend the fabric of reality all around us. What makes the PBH hypothesis so alluring is that it bridges two mysteries at once. Not only could they explain dark matter, but they could also act as relics from the earliest universe, connecting cosmology, gravity, and quantum theory in a way that particles like WIMPs or actions do not. But at the same time, the exotic particle candidates are supported by strong theoretical motivations rooted in particle physics, offering potential insights into entirely new domains of nature's laws. Perhaps the truth is not either or but both. Dark matter might not have a single identity. It could be a mixture, some fraction made of exotic particles, another fraction of primordial black holes. The universe may be stranger than any one explanation can capture, and the final answer could weave together threads from both particle physics and cosmology. For now, PBHs remain one of the most fascinating alternatives, precisely because they take something familiar, black holes, and extend it into the most mysterious corners of cosmic history. Against WIMPs, actions, and other exotic entities, they hold their own as contenders in the grand mystery of dark matter. And whichever of these candidates proves true, the discovery will reshape our understanding of the universe at its deepest level. For all the allure that primordial black holes hold, the scientific community remains cautious, sometimes deeply skeptical, about embracing them as a major part of the universe's story. And this skepticism is not rooted in close-mindedness but in the very nature of science itself. Extraordinary claims require extraordinary evidence. The idea that black holes might have existed before stars, galaxies, or even the Big Bang itself is undeniably extraordinary. Yet, despite decades of speculation, no conclusive observational proof has been uncovered. That absence of hard evidence is a significant challenge. One of the biggest difficulties is that PBHs, by their very nature, are elusive. They do not emit light, they do not radiate in detectable ways unless they're very small and evaporating via Hawking radiation, and they often masquerade as ordinary astrophysical black holes when detected through gravitational waves. This makes it hard to distinguish them from the more mundane stellar black holes formed from collapsing stars. Scientists can measure the mass of a black hole merging event, but they cannot yet pin down its origin with certainty. So, when gravitational wave detectors like LIGO or Virgo register a merger of two black holes, the data does not immediately tell us whether they are primordial relics or the remains of dead stars. Another reason for skepticism lies in observational constraints. Astronomers have been studying the universe's background radiation, gravitational lensing events, galaxy distributions, and gamma-ray signatures for decades. If PBHs were abundant enough to make up all of the dark matter, their collective gravitational effects should have left clearer marks across these datasets. But so far, the evidence points the other way. Large populations of PBHs in many mass ranges seem to be ruled out. For example, microlensing surveys of stars in the Magellanic Clouds haven't found enough events to support the idea of PBHs filling the galactic halo. Likewise, if many small PBHs were evaporating today, we would expect a flood of gamma rays that hasn't been observed. This narrowing of possibilities has led some astrophysicists to argue that PBHs, while intriguing, are not the primary solution to dark matter. They may still exist, but in smaller populations, tucked into niches of mass ranges that are harder to probe. Some see them less as a grand cosmic answer and more as a curiosity that might explain some anomalies but not rewrite the whole narrative of cosmology. Skepticism also comes from the competing weight of alternative theories. For many physicists, the hunt for WIMPs, actions, or other exotic particles remains more promising because these candidates arise naturally from extensions of well-tested physical theories. PBHs, on the other hand, depend on very specific conditions in the early universe, such as unusually large density fluctuations that might or might not have occurred. Without direct evidence, some scientists view PBHs as a kind of cosmic patch, a way of filling gaps in our knowledge without strong justification. Even within the PBH camp, there are disagreements. Some argue that PBHs could only account for a fraction of dark matter. Others believe they may explain only certain unusual black hole populations detected by gravitational wave observatories. Still others see them as unlikely relics, whose possible contributions are too marginal to fundamentally alter cosmology. This diversity of opinion reflects how uncertain the situation really is. At the same time, skepticism does not mean dismissal. Science advances by testing bold ideas, even those that sound radical at first. Many of the greatest breakthroughs, from relativity to quantum mechanics, were once fringe concepts. PBHs remain on the table because they are not impossible within known physics, they are simply unproven. And while evidence against large populations of PBHs is strong, there are still open windows, especially in the intermediate mass ranges that current observations struggle to probe. It's also worth noting that science thrives on caution. If the community were to immediately embrace the PBH hypothesis without strong evidence, it would undermine the rigorous standards that make scientific progress reliable. By applying skepticism, scientists ensure that if PBHs are ever confirmed, the discovery will rest on solid ground, not speculation. So, the challenges are clear: the lack of direct evidence, the difficulty of distinguishing PBHs from other black holes, the strong observational constraints, and the competition from particle physics candidates for dark matter. Yet within these challenges lies the reason PBHs remain so fascinating. If they are discovered, it would not just be another small step in science, it would be a paradigm shift, rewriting our understanding of cosmic origins, dark matter, and possibly even what came before the Big Bang. Until then, the caution, the skepticism, and the insistence on rigorous proof are what keep the search honest, ensuring that when answers come, they will truly be worthy of the mystery they aim to solve. In recent years, despite all the skepticism and the many constraints placed on primordial black holes, a wave of new studies and simulations has kept the idea alive and even reinvigorated it. These investigations have not necessarily proven PBHs exist, but they have shown that under the right conditions, the early universe could have created them in ways that fit within modern cosmological models. What's striking is that instead of fading into obscurity, the PBH hypothesis has become an active area of research, precisely because it ties into so many unsolved problems: the nature of dark matter, the origin of large-scale structure, and the possibility of physics beyond the Big Bang. One major line of research comes from inflationary cosmology, the idea that the universe underwent a rapid, almost unimaginably fast expansion in the first fraction of a second after the Big Bang. Normally, inflation smooths out irregularities, stretching space so evenly that fluctuations are tiny. But in some models, inflation doesn't happen perfectly smoothly. There can be brief phases where fluctuations grow large enough to trigger gravitational collapse. Recent simulations have shown that under specific inflationary scenarios, the density variations in the early universe could have been extreme enough in certain patches to produce PBHs of particular sizes. What's intriguing is that the mass ranges produced in these scenarios sometimes line up with the same ranges where PBHs are still viable candidates for dark matter. Other studies have focused on the physics of phase transitions in the early universe. Just as water can freeze into ice or boil into steam, the universe itself is thought to have gone through transitions as it cooled, with fundamental forces splitting apart and particles acquiring mass. These transitions, particularly if they were violent or uneven, could have produced bubbles, shock waves, and clumps of energy dense enough to collapse into black holes. Modern simulations are increasingly sophisticated, showing how turbulence, bubble collisions, and quantum fluctuations could leave behind gravitationally bound remnants. Some of these remnants might have been PBHs, forming long before stars ever existed. There is also growing interest in the connection between PBHs and the black holes detected by gravitational wave observatories. Since LIGO's first detection in 2015, dozens of black hole mergers have been recorded, many involving objects heavier than typical stellar black holes. Some of these events include black holes around 30 to 50 times the mass of the Sun, an awkward mass range, since astrophysicists expect stars to collapse into black holes of either smaller or larger sizes, but not quite so many in this middle ground. This mismatch has led some researchers to suggest that at least a fraction of the mergers LIGO is picking up could be primordial in origin. New simulations continue to explore whether PBHs could naturally form binaries and merge in just the way LIGO and Virgo have observed. Even more recently, scientists have proposed that PBHs could help explain puzzling astrophysical signals. For example, fast radio bursts, brief, intense flashes of radio waves from deep space, remain a mystery. Some studies have suggested they could arise from PBHs interacting with surrounding matter. Other research has examined whether PBHs could account for strange gamma-ray signals or contribute to unexplained X-ray backgrounds. While none of these ideas has been confirmed, the fact that PBHs are being invoked to explain real observational puzzles shows how flexible and provocative the hypothesis has become. On the computational side, advanced simulations now allow scientists to test a wider variety of scenarios than ever before. High-resolution cosmological models can trace the growth of structure in the universe with stunning detail, revealing how tiny fluctuations evolve into galaxies, clusters, and voids. When PBHs are inserted into these models, researchers can study how they would affect the formation of galaxies, the heating of gas, or the pattern of gravitational waves. Some of these simulations suggest that PBHs, if they exist in just the right numbers, could subtly influence the distribution of matter in ways that might be detectable with upcoming surveys. It's also important to note that in 2019, a bold study proposed that all dark matter could be made of PBHs of intermediate mass, around the scale of asteroid-sized black holes, which are difficult to detect through current methods. Though this claim sparked intense debate and criticism, it reinvigorated the discussion and encouraged new searches designed specifically to target those mass windows. The fact that the hypothesis continues to generate active debate highlights its resilience. Even when many scientists remain skeptical, the door has not closed. Recent theoretical work has even connected PBHs to deeper questions in high-energy physics. Some string theory models suggest that relics from earlier epochs could resemble PBHs. Meanwhile, loop quantum gravity scenarios allow PBHs to form naturally and persist through cosmic transitions. These are speculative, but they demonstrate how PBHs sit at the crossroads of cosmology, quantum theory, and relativity. What ties all of these studies together is that none provides definitive evidence, yet each shows that the conditions for PBHs to form are not as implausible as once thought. They do not require rewriting the laws of physics, just fine-tuning certain processes in the infant universe. The simulations and theories being published today are not so much proof of PBHs but roadmaps showing where to look, what signatures to expect, and how to design experiments that could finally settle the question. So while challenges and skepticism remain, the growing body of recent studies keeps the PBH hypothesis alive. Rather than fading into history as a failed idea, it has evolved into a vibrant possibility, tested and retested against observations, refined by theory, and sharpened by simulations. Each new result, even when it rules out certain mass ranges or conditions, brings us closer to understanding whether PBHs are real or just a beautiful thought experiment. And that pursuit itself drives the next generation of cosmological exploration. The reason primordial black holes matter so much is because they sit at the intersection of the deepest questions in cosmology. These aren't just esoteric curiosities or fringe speculations. They touch on mysteries that have puzzled scientists for decades and continue to shape the entire framework of our understanding of the universe. To talk about PBHs is really to talk about three of the biggest unsolved problems in physics. What is dark matter? How did the structure of the universe form? And what, if anything, existed before the Big Bang? If PBHs turn out to be real, they could hold the key to all three of these monumental questions. Dark matter is perhaps the most famous cosmic mystery of all. We know it's there because galaxies spin faster than they should if only visible matter were present. We see its fingerprints in the way light bends around galaxy clusters, in the cosmic web that binds galaxies into vast structures, and in the fine details of the cosmic microwave background. Yet despite decades of effort, no one has ever detected a single dark matter particle directly. Physicists have proposed candidates like WIMPs, actions, sterile neutrinos, or other exotic particles, but laboratory experiments have not delivered confirmation. PBHs, however, bypass the particle problem entirely. They are purely gravitational objects, needing no exotic new physics to exist. If they were formed in just the right abundance, they could explain dark matter without requiring an entirely new class of particles. In other words, they offer a radical but elegant solution to one of the greatest puzzles of modern science. Then there's the question of cosmic structure. The universe today is filled with galaxies, galaxy clusters, and immense filaments of matter stretching across billions of light-years. But how did all of that begin? Small fluctuations in the density of the early universe grew under the influence of gravity, eventually becoming stars and galaxies. Yet scientists still wrestle with why certain structures formed so quickly and why galaxies seem to be distributed in the patterns we observe. PBHs could play a role here too. If they existed in the early universe, they could have acted as seeds, around which gas and matter clumped together faster than they would have otherwise. They may have accelerated the birth of galaxies, perhaps even determining their distribution. In this way, PBHs aren't just potential dark matter, they may be written into the very blueprint of cosmic architecture. The third great question, the most audacious of them all, is whether the Big Bang really was the beginning. Standard cosmology treats it as the ultimate starting point, the moment when space, time, and matter came into being. But if PBHs exist, they might be older than the Big Bang itself, relics of a previous cosmic era that survived into our own. This would mean the Big Bang wasn't the true beginning, but rather a transition. PBHs could act like fossils from a pre-Big Bang universe, holding clues about conditions and physics we cannot otherwise probe. They might even help distinguish between competing cosmological models, such as whether our universe emerged from a bounce, a cyclic pattern of births and deaths, or a higher dimensional process predicted by theories like string cosmology. If PBHs exist in mass ranges that cannot be explained by post-Big Bang processes, it would be one of the strongest hints that something came before. Why does this matter? Because science is ultimately about origins, where we came from, why the universe is the way it is, and whether its story stretches further back than we've ever imagined. PBHs offer a rare chance to tie together threads that often feel separate: galactic evolution, gravitational waves, dark matter, and fundamental physics, into one coherent narrative. They provide a bridge between the known and the unknown, between the universe we observe and the mysteries still locked in its earliest moments. There's also a profound philosophical reason this matters. For centuries, humans have sought to understand their place in the cosmos, and each time we've uncovered something new, the picture has become stranger and grander. Discovering PBHs wouldn't just explain numbers in equations. It would force us to expand our conception of reality itself. It would mean our universe is not simply a product of the Big Bang, but part of a deeper cosmic story that stretches beyond that horizon. To many scientists, this possibility is what makes the search worth it. Even if PBHs turn out not to exist, the attempt to find them pushes us to develop sharper theories, build more sensitive detectors, and think more boldly about the cosmos. But if they do exist, they could provide the missing link that unites multiple mysteries into a single framework. In that sense, PBHs matter because they might change everything: our view of dark matter, our understanding of how galaxies formed, and our belief about whether the Big Bang was truly the beginning of all things. The question of primordial black holes has always hovered at the boundary between speculation and science, but the future promises something extraordinary: the ability to either confirm their existence or finally close the door on them. For decades, PBHs have lived in the realm of theory and indirect hints, but with a new generation of telescopes, gravitational wave observatories, and sky surveys, we are entering an age where the universe can be probed with a level of precision that was unthinkable only a few decades ago. If primordial black holes exist, the coming century of observational astronomy may well be the time we finally catch them. One of the most promising avenues comes from gravitational wave astronomy. The LIGO and Virgo detectors have already changed the landscape of physics, picking up the ripples in spacetime created by colliding black holes and neutron stars. But this is only the beginning. New detectors like Kagra in Japan are joining the network, and the planned Einstein telescope in Europe and Cosmic Explorer in the United States will be far more sensitive, capable of detecting mergers at much greater distances and across a wider range of masses. Even more ambitious is LISA, the Laser Interferometer Space Antenna, a space-based observatory scheduled to launch in the 2030s. Orbiting in space, LISA will be able to pick up gravitational waves from entirely different classes of objects, including smaller black holes and even possible signals from PBHs formed in the very early universe. If PBHs exist in abundance, These observatories could reveal them not only through mergers but through their subtle gravitational signatures. Another critical path lies in sky surveys that look for microlensing events. When a massive object passes in front of a star, it bends and magnifies the light in a predictable way. If PBHs are abundant, especially in certain mass ranges, they should occasionally drift in front of stars and produce microlensing signals. Projects like OGLE and MACHO in the past looked for such signals and constrained certain mass windows, but the next generation of surveys will take this to an entirely new level. The Vera C. Rubin Observatory in Chile, with its Legacy Survey of Space and Time (LSST), will scan the sky with unprecedented depth and frequency. Over a 10-year mission, it will produce a movie of the dynamic universe, catching rare microlensing events that could reveal the presence of PBHs with masses ranging from that of asteroids to stars. In combination with surveys from space telescopes like Euclid and the Nancy Grace Roman Space Telescope, we will soon have an extraordinary data set to either confirm or tightly rule out large populations of PBHs. The cosmic microwave background, CMB, remains another powerful tool. The faint afterglow of the Big Bang carries within it subtle imprints of everything that happened in the early universe. PBHs, if present in significant numbers, could leave behind tiny distortions in the CMB's temperature and polarization patterns. Current missions like Planck have already placed constraints on certain PBH populations, but upcoming experiments, CMBS-4 in the United States, the Simons Observatory, and possible space-based missions like LIGHT-BIRD, will take precision measurements to a new level. These instruments could detect even fainter signals, revealing whether PBHs left their fingerprints on the oldest light in the cosmos. High-energy astronomy may also play a role. Small PBHs would slowly evaporate through Hawking radiation, giving off bursts of gamma rays in their final moments. Gamma-ray observatories like NASA's Fermi Gamma-ray Space Telescope have searched for such signals and placed limits on how many small PBHs can exist, but more sensitive detectors in the future could take this search further. The Cherenkov Telescope Array, CTA, under construction now, will be the world's most advanced gamma-ray observatory, capable of detecting the faint high-energy emissions that could betray evaporating PBHs. If even a few survive to the present day, CTA might be able to catch them in the act of disappearing. And then there's the possibility of indirect detection through astrophysical puzzles. Already, PBHs have been invoked to explain the unusual masses of some black holes observed by LIGO, the distribution of fast radio bursts, and unexplained cosmic ray signals. Future instruments may detect more of these anomalies, giving scientists more opportunities to test whether PBHs are the culprit. Sometimes science advances not by finding what you expect, but by noticing what doesn't fit, and PBHs are often the misfit explanation that could tie things together. It's worth emphasizing how powerful this next generation of technology really is. For most of human history, black holes were purely theoretical. For much of the 20th century, PBHs were little more than mathematical curiosities. Now, in the 21st century, we have instruments capable of detecting ripples in space-time, faint distortions in the oldest light, gamma rays from across the galaxy, and the bending of starlight by invisible objects. All of these methods can be applied directly to the question of PBHs. This is an unprecedented convergence, a set of independent, complementary approaches all zeroing in on one mystery. If PBHs exist, it will be nearly impossible for them to hide for much longer. But the most exciting part of this future isn't just the possibility of confirmation. It's what confirmation would mean. If even a small population of PBHs is detected, it would ripple across physics. It would provide a natural explanation for at least part of dark matter, challenge our assumptions about the early universe, and open a window onto physics we cannot test in laboratories on Earth. And even if PBHs are ultimately ruled out, the process of searching for them will sharpen our understanding of dark matter, inflation, cosmic structure, and black holes themselves. Either way, the quest pushes science forward. So the future of detection is not merely about proving PBHs right or wrong, it's about using the best tools humanity has ever built to probe questions at the edge of existence. The next few decades promise discoveries that could transform our understanding of the universe. And hidden within those discoveries may be the answer to whether primordial black holes, those cosmic ghosts from before the dawn of time, are truly out there. Throughout this long journey, we've traveled from the heart of a mystery to the edge of imagination, following primordial black holes across theory, observation, and speculation. We've explored what black holes are, how the primordial ones differ from the stellar kind, the seething conditions of the early universe, and the tantalizing possibility that some of these objects could have existed even before the Big Bang itself. Along the way, we've seen how they may connect to the enigma of dark matter, how they might have seeded galaxies, how they could hold clues to cosmic cycles, and how new telescopes and observatories might finally reveal them. Each step deepens the sense that PBHs are more than just another scientific idea. They are a lens through which we glimpse the possibility that our universe's story is not what we thought it was. Think for a moment about the scale of what's at stake. If primordial black holes truly exist, then they are relics that have survived unimaginable cosmic upheavals. They would be older than the first stars, older than the first galaxies, older even than the very expansion we call the Big Bang. To find one would be to hold a fossil not of bones or rocks, but of the universe itself, a direct piece of evidence from a time no human, no probe, no telescope could otherwise see. It would be like discovering that the universe has been keeping diaries, and PBHs are its secret journals, locked away in darkness for billions of years. And what if those journals tell us that the Big Bang wasn't the beginning? That there was something before, whether another universe, a collapsing cosmos that bounced back, or a higher dimensional reality whose echoes we still feel? The discovery of PBHs might not just answer questions. It could rewrite the very narrative of cosmic history. It could mean that the universe has a memory, that there were chapters before ours, that existence stretches back further than we've ever dared to believe. Suddenly, before the Big Bang ceases to be a philosophical musing and becomes a scientific frontier, a realm where gravity, quantum mechanics, and the fabric of space-time all converge. Even the smallest PBH, the size of an atom but as heavy as a mountain, would be a monument to the power of nature's laws. Even the largest, thousands of times more massive than our Sun, would carry within it information about conditions that existed when the cosmos was still in its infancy. These objects are both terrifying and beautiful, singularities wrapped in mystery, yet offering answers. They remind us that the universe is not built for our comfort or comprehension, but for its own astonishing purposes, and that our role is to explore, to wonder, and to seek understanding. It's humbling to realize that right now, as you listen to this, there could be primordial black holes drifting silently through space. Some could be hidden in the dark between galaxies. Others could be wandering through the outskirts of our own Milky Way. One might even be passing unseen through our solar system, leaving behind only the faintest gravitational trace. They may be everywhere, unnoticed, shaping the cosmos from the shadows. The fact that something so ancient and fundamental could be all around us without our direct knowledge is a reminder of how vast the unknown still is. Science thrives on such mysteries. It is the spark that drives us to build gravitational wave detectors that listen for ripples in space-time, telescopes that scan the sky for flickers of bent starlight, and satellites that map the universe's earliest light. Whether or not we find PBHs, the search itself enriches us. It reminds us that the universe is not static but alive with questions, and that humanity is uniquely equipped to ask them. And so we return to that haunting idea: what if some black holes existed before the universe itself was born? It sounds impossible, like a paradox or a myth. But it's precisely these kinds of ideas, the ones that stretch imagination to its breaking point, that sometimes turn out to be true. And if it is true, then perhaps our universe is not a short story that begins and ends with the Big Bang. Perhaps it is part of a grand epic, one that has chapters we have not yet read and twists we cannot yet predict. So let us end not with an answer, but with a sense of wonder. If primordial black holes really did exist before the Big Bang, then maybe our universe's story is far older and stranger than we ever imagined. And maybe, just maybe, the darkness we fear is not empty at all, but full of secrets waiting to be uncovered. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.